one of the greatest mathematical minds in history. I invite our director, Sir Professor Rajiv Prakash, our invited speaker, Professor Arup Bose from ISI Kolkata, Dr. Abhijit Pal, the Associate Head of the Department of Mathematics, Dr. Kuldeep Kumar Kataria, DPGC Mathematics, Dr. Rajkumar Mistry, the convener of National Mathematics Day 2024 to dais and request them to take their respective seats. Thank you everyone. To mark the beginning of today's event, we will commence with the lighting of the lamp. Now I request our director, Sir Professor Rajiv Prakash, to light the lamp and inaugurate the celebration. Also, I invite our invited speaker, Professor Arup Bose, and the other dignitaries on the dais to join him. Thank you, sir, for lighting the lamp and illuminating the path for this wonderful event. To begin, I request our director, sir, Professor Rajiv Prakash, to welcome Professor Arup Bose with a bouquet of flowers. Thank you, sir. We have two more invited guests, Professor Ritabrata Munshi and Professor Kalyan Chakravarti, who have joined us virtually. Let us now warmly welcome Professor Ritabrata Munshi with a bouquet of flowers. Now we welcome Professor Kalyan Chakravarti with a bouquet of flowers. Next, I would like to request the Associate Head of the Department of Mathematics, Dr. Abhijit Pal, to welcome our Director, Sir Professor Rajiv Prakash, with a bouquet of flowers. Thank you, sir. Now I request Dr. Kuldeep Kumar Kataria, DPGC Mathematics, to welcome the Associate Head of the Department of Mathematics, Dr. Abhijit Pal, with a bouquet of flowers. Thank you, sir. Now I request the convener of today's event, Dr. Rajkumar Mistry, to welcome DPGC Mathematics, Dr. Kuldeep Kumar Kataria, with a bouquet of flowers. Thank you, sir. Finally, I request Vivek Anand to welcome the convener, National Mathematics Day 2024, Dr. Rajkumar Mistry, with a bouquet of flowers. for his welcome address.
Good morning everyone. Honorable Director Professor Rajiv Prakash, the chief guest of this program, respected guests and dignitaries, esteemed faculty members, staffs, students, media persons and friends. On behalf of the Department of Mathematics, I.I.T. Bhilai, it is my honor and privilege to welcome you all to this special occasion as we celebrate National Mathematics Day 2024. We are delighted to have with us three eminent speakers, Professor Arup Bose and Professor Munshi from ISI Kolkata and Professor Kalyan Chakravarti from SRM University AP, who are leading mathematicians in their fields. Welcome all of you, sir. National Mathematics Day is celebrated in India on December 22nd every year to honor the legendary Indian mathematician Srinivas Ramanujan. This day commemorates his birth and recognizes his immense contribution to mathematics, particularly in areas like number theory, infinite series, and continued fractions. Ramanujan's work has had a profound impact on modern mathematics, and his legacy continues to inspire mathematicians and students around the world. National Mathematics Day serves as a reminder of the importance of mathematics in shaping various fields from science and engineering to economics and technology, and encourages young minds to explore the beauty and relevance of mathematical research. These events mark the 137th birth anniversary of Srinivas Ramanujan, and it is the first event on National Mathematics Day celebrated in the permanent campus of I.I.T. Bhilai, and the fourth National Mathematics Day event of the I.I.T. Bhilai. The event is significant because this is the first time we are celebrating this event in the presence of faculty members of various colleges across the country. The program will have two sessions. There will be exciting quiz competition after the first session. The quiz will be on life and history of eminent mathematicians and general mathematical concepts. I hope you will enjoy the program. Once again, I extend my warm welcome to all of you. Let us make this day a memorable one as we celebrate the incredible world of mathematics and honor the legacy of Srinivas Ramanujan. Thank you, and let us have wonderful moments, and thank you.
Thank you, sir, for your warm and welcoming words. As we continue with our event, I invite the Associate Head of the Department of Mathematics, Dr. Abhijit Pal, to address the audience.
Hello. So, dear Honorable Director Sir, Professor Rajiv Prakash, dear distinguished guest, Professor Arup Bose from ISI Kolkata, Professor Munshi from ISI Kolkata, and Professor Kalyan Chakravarti from SRM University, Andhra Pradesh. So, dear Dr. Kuldeep Kumar Kataria, dear Dr. Rajkumar Mistry, dear Zoa, Dr. Dhruv Prakash Singh, and my colleagues, and dear participants, media persons, students. So a very good morning to all of you. Today we assemble here to celebrate the National Mathematics Day. So this is the 137-year birth anniversary of great mathematician Ramanujan. Ramanujan is considered one of the greatest Indian mathematicians of all time. His works includes his infinite series of pi, theory of prime numbers, and modular functions. He also contributed to the number theory and infinite series. So Ramanujan was born on December 22nd, 1887, and died on April 26, 1920. So he had little formal training in mathematics, but he discovered thousands of identities, equations, and theorems on his own between 1903 and 1914. In 1914, he traveled to England, where he collaborated with G.H. Hardy and Littlewood. So Ramanujan's mathematical discoveries are still relevant today. His work is considered to be elegant, deep, and surprising. It is also said that Ramanujan's life and work demonstrate what the human mind can achieve. So I want to make some quote from Ramanujan. An equation for me has no meaning unless it expresses a thought of God's. So he is a very big mathematician. So thank you and welcome to everybody. And so I will end that talk with that. Okay, thank you very much. And
Thank you, sir, for your insightful address. It's my pleasure to welcome our director, sir, Professor Rajiv Prakash, who has kindly made time from his busy schedule to be with us today. Sir, may I request you to address the gathering?
Thank you very much and very good morning. Professor Bose, who is present here, thank you for coming and gracing this function. A great day. Bharatiya Ganit Divas, National Mathematics Day. This is the time when we get this opportunity to remember our great history through Ramanujan ji. And from here, you go back in history from Vedic mathematics and how rich knowledge this India, this country was having. On this occasion, I also welcome two eminent speakers, Professor Munshi and Professor Chakravarti, those who are joining online. And friends, I am once again welcoming you, our faculty member, our own faculty member from I.I.T, Bhilai students, and others from different part of country, the teachers here sitting in this hall. I congratulate you for this day, and I hope that this two-day conference will be really fruitful, and you will get time with this, our eminent speakers, mathematicians are here to interact with them and take many more things to back to your home. Unfortunately, holiday period is going on, so we will not get much participation of students, but I am quite hopeful that PhD students, those who are on the campus, they will interact with you all and especially with our speakers. And this is the two-day program is scheduled in a way that here the lectures, quizzes, and many other competitions. I hope that you are planning for these 2 days. So wonderful. Friends, again, I would like to emphasize 1 or 2 minutes on this topic, or mathematics topic, which is not my domain. I can't say much when Professor Bose is himself sitting here. So, but you all will realize one thing. Whatever we have knowledge system, this is unfortunately not delivered to our present current generation in the way as it should be. I think you all will agree. In any area, whether it is mathematics, physics, science, humanities, arts, history, any area, if today we are talking in our class, what is the first class we are giving is a schedule, is a planned syllabus lecture, unfortunately not connecting with our knowledge system, what the India was having, that we call the Bharatiya Gyan Parampara. In this, the role of Vedic mathematics is great. Many times I am giving example, when the 16th century Western scientists were trying to calculate the distance between Earth and Sun. See, before how many centuries our mathematicians have proved this distance. They were talking about a whole universe. And in 16th century, the Western worlds, they were trying to know the distance and trying to know who is revolving Earth or the Sun. We all know. So, in Vedic mathematics, why not, if you are starting your class, then you start from Vedic mathematics. Why not give the knowledge to our students, to our great culture, great history, and the knowledge system? Then they will realize. You all know that the same multiplications or division, a simple example I am giving, or a square root calculation using this modern mathematics way, and if I compare this with the Vedic mathematics way, how fast we can do this. So within a few seconds you can find out the difficult calculations of a square root or the multiplication. So this is a simple example. I am not talking about the great theorems which we are proving our Vedic mathematics style and the new mathematics. So why not introducing our students with this? So this initiative I am trying to start, and I think most of our faculty members, they have already started. When you are going to first in your class to introduce with our knowledge, which country, which India was having, aware with them, and then come back to your syllabus. I am not saying, but this should be the part of your syllabus. If students will not know who is Visvesvaraya, who is Ramanujan, then certainly if in interview sometime I used to ask, Visvesvaraya ji was known for what? No. See friends, if you will find this corridor, if you move this in this corridor, you will find many nice structures. Professor Bose, you will find these corridors. These are taken from here, this area, the Gond art, this is the local, and each structure is having some story behind that. And so when you will go through these, students will, in curiosity, they will try to find out what is this, and they will connect with our history, with our rich knowledge. Similarly, if you see the name of the halls, someone is a Nalanda hall, some of the Vishwakarma buildings, why? Motive is only one. If you want to tell about your great history and knowledge, then students should aware with this first name, okay, and then what is this, then they will try to find out, oh, why Nalanda? What is the reason of Nalanda? Why Takshila? Why Takshila? Then they will know that when the whole world was knowing nothing almost, that time we were having universities like Takshila and Nalanda, and we were rich in knowledge, and that still we didn't achieve so far. You are here mathematicians, great mathematicians. No need to tell that today if our students are known that they are sharp, they are brilliant. The one point is very much common. Everyone is saying whenever I am visiting any abroad university and institute, your students are very good in mathematics. So I met a group of mathematics teachers in Ireland, in one of the university. Young faculty members, they were associate professors there. And they said, sir, you know what our administration is saying, you keep the mathematics little bit slow, and because our students are not as brilliant as your Indian students. See, such a proud moment. I felt that our students are known for their skills and knowledge in mathematics. Brilliant students, and this is because of all of you, who the teachers, teaching them from primary, and how you are teaching them the mathematics and bringing them up to this level. Also, I am saying to our young faculties, especially for the mathematics faculty, friends, this is time when mathematics is doing a lot in many areas. If you talk about AI and ML algorithms and all, who can do better than others? Is the mathematicians who can do. I'm also telling them yesterday or day before yesterday, I was discussing to Kuldeep that why not you are making some programs, some small crash programs, as the people coming from all from different places, and they are taking here study programs. We can deliver them at home, and just a 5 days program to 5 months program, and we design like this. And they can do this because I know that our mathematics department is doing very well. Yesterday program also, you appreciated that how the teachers are teaching, our mathematics teachers. I know our students. So we have potential here, and when such eminent professors are associated with us, then it is not difficult that what we are planning, we are thinking at IIT Bhilai, we can go ahead. Friends, I will not take much time because I know, I understand that you people are here to discuss, to interact with our speakers, with our colleagues, and in this area, mathematics and other quizzes. But with this hope that what the rich knowledge we were having, what the requirement of our present students, and in the way how they want learning, teaching, learning. So think and let us start. This is the right time that we should do. Thank you. Thank you very much.
Thank you, sir, for your encouraging words. We truly value your presence and the insights you have shared with us today. Now I request all the dignitaries to take seats in the front. Thank you, everyone. To moderate the first session of this event, I request DPGC Mathematics Dr. Kuldeep Kumar Kataria on the stage.
So, good morning everyone. So, it's my honor and privilege to introduce the invited speaker, Professor Arup Bose. So, I will give a very brief introduction about him. So, let me ask my forgiveness if I miss something crucial, sir, because the list is big, okay? So, and it's very definite that there may be some error, okay? Yeah, it will be brief. So Professor Arup Bose is a distinguished statistician with an impressive academic background and career. He earned his B.Stat, M.Stat and PhD degrees in statistics from Indian Statistical Institute, Kolkata. After completing his PhD, he joined Purdue University in USA as an assistant professor, where he worked for 4 years before returning to India in 1991. Upon his return, he joined ISI Kolkata, where he has made significant contribution in his field of research. Professor Arup Bose provided extremely novel applications of results from stochastic processes to derive asymptotic properties of maximum likelihood and Bayes estimates in nonlinear diffusion processes. He provided a unified and comprehensive study of deep convergence properties of existing and new bootstrap and resampling scheme in a variety of estimators and models. He obtained higher order properties of a collection of sequential estimates in a very general framework. He achieved deep limiting results for U statistics. He constructed a unified limiting theory of patterned random matrices. His recent book, Random Matrices and Non-Commutative Probability, is highlighting his many contributions to the field. He is a member of Bernoulli Society for Mathematical Statistics and Probability, Netherlands, life member of Calcutta Statistical Association, and a life member of Indian Mathematical Society. Professor Bose's work has been recognized with several prestigious honors. He was awarded the Santi Swarup Bhandnagar Prize for Science and Technology in 2004, the highest science award in India, in the mathematical science category. He was an invited speaker in International Congress of Mathematicians 2010, Hyderabad, on the topic of probability and statistics. Among his other honors includes he is elected fellow of the Institute of Mathematical Statistics, USA. He received National Award in Statistics in honor of Professor C.R. Rao for the year 2002-2003. He is a Young Researcher Award, International Indian Statistical Association, Fellow of Indian Academy of Science, Fellow of Indian National Science Academy, Fellow of the National Academy of Science. He is a JC Bose Fellow, GST Government of India, and Bernoulli Society Council member. His scholarly influence extends to international academic circles, and he serves as a member of several renowned national and international journals. His contribution to statistics and academia have solidified his reputation as a leading figure in the field. Please join me in welcoming Professor Arup Bose for delivering today's talk on partition trees, and random matrices.
Slides, I mean. So while we wait, thank you all for coming to listen to my talk. I have sent it. They said they have loaded in the video. Sir, follow me. I don't think so. I think it's fine. It's right here. Okay, no, the other is in there. Sure. So I noticed that many of you have the same T-shirt. What is that about?
सर वो डाउनलोडेड नहीं है क्या? मैं डाउनलोड कर नहीं वो दूसरे किसी
So I'll He's undergraduate student. So obviously she actually is a lady. She didn't know how to write a paper. But there's some excellent ideas and many papers have come out of that work. So, I mean, you learn a lot of things from your students. It's, often it is the other way around. The students learn less from you than you learn from them. It's because it depends on how you interact with them. You open their minds and they will give you ideas. Of course, the next generation is much smarter than us. They know more than us. They can Google more than us. Okay, so they have many more ideas. So every researcher should keep this in mind. That teaching is primary, research is secondary. And when it comes to research, of course, now times have changed, things have changed. So research should be, it was not in our times, research should be oriented towards the benefit of mankind. So even in mathematics, you should think of course, you are interested in some very abstract area, that's fine, that's great. Some people can think abstractly, they have this gift, not everybody can. So you contribute to that. But at the same time, because you are skilled, how many PhD scholars are there in the country? How many PhD holders? Not many if you think of the population of India. So we have a special place and we should use that. We should use that to collaborate with other areas like physics, like chemistry, like biology. They are all using maths. And because of want of good mathematicians, they are working on their own and they are producing something. If you join hands with them, you have to learn their language a little bit. They have to learn your language a little bit. So that's a friendship which is worth taking, and that's where how the science and mathematics also, they will discover some new problems from there also. So for example, when I have worked in different areas, I've kept my mind open. Somebody comes to me and talks to me about some areas. he or she is welcome to me. And then very often I have used some result from one area in some other area. That very often happens. But you have to keep your mind open. As Paul Edwards has said, my brain is open. Okay. So with that brief words, did you get the slide? Alright, so my training has been in statistics, but I probably would have been a more theoretical mathematician if my training was as good in statistics as it was not as that good in maths, unfortunately. But I like mathematics, I love mathematics, and I interact with mathematicians. So today I'm going to wear the hat of the mathematician. My talk is going to be on partition trees and some combinatorics. So in some sense it's connected to number theory. It's really not number theory, but it's more a little bit of combinatorics. And try to keep my work, my slides, my talk simple enough for most of you to follow. Maybe the undergraduates, if there are any undergraduates, maybe they will find it a little bit difficult. But I have tried to couch my slides in the language of maths more than in language of probability. So I hope all of you will be able to follow it. If you have any questions in the middle of the talk, you can raise your hands. There's a board here also. I can explain things on the board also. Better? Okay, call mic. What happened to the screen? This is also gone black. So there's a request for caller mic. Okay, can you hear me? Yeah, okay, very good. Okay, maybe we should put this off then. Let's go off. Okay. So I should use this one or this one is okay? No, it's going back. Yeah. Okay. Yeah. Yeah, I will use that. Okay. Huh? This is back. Okay. All right. Okay. All right. So they will not allow me to put out the first slide. It's fine. We start for number 2. Okay. So here's a quick outline. partitions. So I'll talk about a little bit about Poisson measures. Many of you in mathematics, especially who work in harmonic analysis, would know the Poisson measure. The Gaussian measure, of course, same. And what is known as Isserlis's formula. It's a formula from 1918, so more than a century ago. But it sort of have been forgotten. And like in many other formulas and theorems, they go by the name of not the discoverer but somebody else. So Isserlis's formula is known as Wick's formula in physics, because Wick was a famous physicist and he used this formula in physics. So they have taken out the name of Isserlis and it goes by Wick's formula. So I'll explain what that is. And then non-crossing partitions. So there is what is called a semicircle probability measure, which is also known as a free Gaussian probability measure. And then I'll talk about special symmetric partitions, colored rooted trees, and then connection with random matrices, which is my primary area of interest these days. And I'll talk about a little bit about Wigner and sparse Wigner matrices, and then some other random matrices. Probably I will not talk about this topic. Okay. So for some people who may not be familiar too much with the language of probability, there are some initial slides. So P is a probability measure on R. So like any other measure, P, you call a measure to be a probability measure if the total measure is equal to 1. The moment generating function of P is defined as mt equal to the integral of e to the power tx. Okay, of course I'm assuming everywhere in this talk that these moment generating functions are finite in a neighborhood of 0. That is assumed there. So of course you can expand this exponential and you can write that integral as a power series. So these coefficients here are called the moments of the measure P. So if you change P, your moments will of course change. So I'll denote that those moments by Mn. Even though these depend on P, I will not mention that dependence of P here. Strictly speaking, I should write Mn of P. So for any probability measure, if I take the integral of x power n, then that is called the moment of P. And you can get back the moment generating function. Or you can, if you take a minus here, it's really the Laplace transform of the measure, right? So if you had this probability had a density, then this would be e to the power tx fx dx. That's more familiar territory for harmonic analysis, where you have a function, you take the integral or the Laplace transform of that function. The variance of P is defined as n2 minus m1 squared. That's an important object in statistics and probability. Let's not worry too much about that. But at some point, I'm going to use that word, so that's why I wrote that. The cumulants of P are the coefficients in the expansion of. So you take this function mt t in a neighborhood of 0, and you, because it's a non-negative function, you can take the logarithm. So you take the log and you expand it. Then these coefficients, just like this expansion, these coefficients Cn's are called the cumulants of the probability measure P. And of course, because you are using the same function m here and the log of m here, these coefficients Cn and these coefficients Mn have to be related to each other. In fact, they have to be in one-to-one correspondence, because this is a one-to-one function, right? Log or exponential is a one-to-one function. Okay, so my first business is to show you how these sequences Mn and Cn are related. And that is via some very beautiful combinatorics. Before that, let's see some examples. So the first three moments and cumulants. Recall, Mn is the nth moment, Cn is the nth cumulant. It can be checked by equating coefficients that m1 is equal to c1, and proceeding further, m2 is equal to c2 plus c1 squared. So the variance, remember, was m2 minus m1 squared, so which is equal to c2. So the variance is actually the second cumulant of the measure. So of course, observe that the set 1, 2 has two possible partitions. So remember my goal. What is the relation between the sequence Mn and the sequence Cn? So I am trying to explore. So M2 is like this. Now observe that this set 1, 2 has two possible partitions. So we are getting into partitions of sets. So one partition is the whole block, one block partition, and the other partition is the single two blocks partition. Okay. Now suppose that for M2, for this block partition, there are two objects here. So I'll put C2 here, and I'll put C1 here and C1 here and multiply them. So C2 and C1 square. That's how it turns out to be. But there is of course no real logic. Yeah, it just so happens like that for the moment. It can also be checked that N3 is equal to C3 plus C2 C1 plus C1 cube. That's not very hard to do because the first three you can take the derivative and equate to t equal, put t equal to 0 and calculate. Observe that 1, 2, 3 has 5 possible partitions. Here is a list of all the partitions. And for this one block partition, now I'll take C3. See this, for this two block partitions, I'll take C1, C2. So C1 times C2, and it appears 3 times. And this one will give me C1 times C1 times C1, C1 cube. So you get C3 plus 3C2 C1 plus C1 cube. That also just happens to be like that. And that is actually the general formula. Any moment can be written in terms of cumulants like this. So what do I mean by like this? Let's make it more precise. So S is in general, S is a finite totally ordered set like 1 to up to 20. And pi is a typical partition of S. So setting up notations here. Mod pi is the number of blocks of pi. So any pi is a partition. Like 1, 2, 2, 3 is a partition. And mod pi is the number of blocks. And V1 to Vr are the blocks of pi. And hash AA will denote the number of elements of any set A. So Zn and its partition for every n bigger than or equal to 1, S, so I'll use S equal to Zn. The reason for writing down the general S is that whatever I'm doing for this Zn can also be done for general, what I call the partially ordered sets. So let's not worry too much about that. So I'll put Zn here and with the natural ordering. And Pn is a set of all partitions of Zn with the reverse refinement partitioning order. So for example, 0n is the n block partition. So if I take 1, 2 up to n, so the n blocks 1, 2, 3, 4, all these, so that's an n block partition. I'll think of that as the smallest partition. And the 1 block partition, 1, 2 up to n, which is the 1 block, that will be thought of as the largest partition. Of course, not all partitions are, you can order them, but there is a partial order you can see. So 0n is less than 1n. So now, if you remember the example that we did, we were taking products of C's, C1, C2 square and all that. So that idea is made formal here in this slide via what is called the multiplicative extension. So for any probability measure or random variable, there is a combinatorial relation between Mn and Cn as follows. So define the multiplicative extension as follows. So I had a sequence Mn indexed by n equal to 1, 2, 3. For every n, I had a sequence Mn. So they were the moments of a probability measure. They don't have to be. You can start with any sequence xn. And I am now extending that sequence xn to a sequence indexed by partitions. So for every partition pi, so remember pi is broken up into blocks v1, v2, vr. So I'll take the sizes of these blocks. So maybe v1 is of size 2, then I'll get m2 here. v2 is of size 4, then I'll get m4 here. And you take a product of those m's. Alright? So then that is known as m pi. And similarly, as I said, for every sequence you can define that. So if you have a sequence Cn, you can define the multiplicative extension of C. So now, from sequences indexed by integers, I have gone to sequences indexed by partitions. Now because n is arbitrary, so this can be any block size. Okay? For example, if pi1 is equal to 1, 2 and pi2 is 1, 2, then m pi1 is m2 and m pi2 is m1 square. So denote the 5 partitions of 1, 2, 3 as tau 1, tau 2, tau 3, tau 4 and tau 5, or tau 4, I think I'm missing here, this is tau 5. So m tau 1 is m3, m tau 2 is m tau 2, they are all equal, m1, m2, and m tau 5 is m1 cube, right? Very clear. So this has 1, 2, 3 blocks here, so each of side C1, so that's why you get m1 cube. So you could do it for any sequence. For our purposes, it's being done for moments and cumulants. Okay, so here is the first result, that Mn can be expressed in terms of Cj through their multiplicative extensions as follows. So you look at Mn and look at all cumulants, all multiplicative extension of cumulants, where you take the set 1 to up to n, and you look at all possible partitions. So this is trivially, all partitions are less than or equal to 1 in the big block, one block partition. So you sum over all possible multiplicative extensions of C pi, you'll get back Mn. Okay, so this is not very hard to prove. You can prove it by induction. So we have checked it for n equal to 2 and 3, right? So you assume it for n and you try to prove it for Mn plus 1. How do you do that? You take the derivative of the Montgomery function and derivative of the, and then you can, assuming it for n, you can prove it for n plus 1. It's not very difficult to prove. You should try and prove it.
So this is for all n greater than or equal to 1, right?
This is for all n greater than or equal to 1. So in particular, M1 is C1, of course. Yeah, and M2 will be C1 square plus C2, because there are only two partitions, like the two examples that we have seen. And M3 will be C3 C1 cubed plus 3 C1 C2 plus C3. Okay, because there are 5 partitions there. So number of terms will depend on how many partitions of 1 to up to n you can get, and that is known as the Bell number. So more generally, on the left side also I can have sigma. So the multiplicative extension. Now instead of all partitions, I have to sum over only partitions which are smaller than or equal to sigma. Okay, so that is the general form. So this is the relation of getting back moments from cumulants. What about the other way? Of course, it's a one-to-one relationship. So this relation must be invertible. How do I see that? Okay, I'll not give a complete proof, but this is how you do it. So look at this relation. Okay, this is a linear relation, right? If you think of indexing by partitions, this is a linear relation. So look at all possible. So fix n. Okay, if I can do it for every n, that's fine. So fix n. Look at all partitions sigma of 1 to up to n. So for every such sigma, you get m sigma as being obtained from C pi. So no chalks here. There are pens. Okay, anyway. In the whiteboard. Okay, right, of course, yeah. Yeah, so I think I will prefer this one. Yeah, good idea. Okay, thanks. So you fix n, so you have 1 to up to n, and you take any sigma here, and then you have written it as C pi less than or equal to sigma. Okay, so m pi is sigma is that. So now enumerate all these, all the partitions of 1 to up to n. There are a lot of partitions, but for every partition we have this. So you can think of this vector of m's. Okay, the smallest partition you can take. So m0 is here, or I think I denoted by 0, and you have m1 in here, and there are some things in between. Okay, and on this side you have a matrix, and that matrix looks like the following. You see, so before that I will write C0 here, and then C1n here. Okay. Now if you look at that, you'll see I am summing over all pi less than or equal to sigma, which means, so here I have the first partition, and then I have some kind of ordering. And the way I'll do the ordering is that I'll make sure that anything which appears to the right of something is either not ordered, or if it is ordered, then it's bigger than that. I can do that. So some kind of ordering I have fixed here. Then you will see that you see pi. So anytime you have a pi here and a sigma here, where pi is less than or equal to sigma, then you get a 1 here. Right? That's precisely what that is. So in the diagonal, you'll get all 1s. And then you get some 1s here, and then you get a 0 here. Because this sum is not over pi bigger than sigma any time. Okay, so now what kind of a matrix is this? This is the upper triangular matrix with all diagonals 1, which is invertible. So you take the inverse of that matrix, then you have written C as a function of m. Okay, and so that matrix, so if I call this A, that matrix A inverse, so again I can think of that, any element of that as A of sigma pi, right? Because there is index by where sigma is less than or equal to pi. So that function is known as the Mobius function. So those who work in combinatorics will identify this as the Mobius function. Okay, that's all. So this relation can be inverted so that Cn can be written in terms of Mj and j less than or equal to n via the Mobius function on the lattice of partitions of Zn. So that, of course, that relation is not that easy to write down because it's not easy to calculate this Mobius function.
So we don't have a closed form.
We don't have a closed form, no. Yeah.
So this relation between Mn and Cpi, this is proved by mathematical induction after observing the...
Yes, this can be proved by mathematical induction. This needs a little bit, I mean, from here you can go there, but this you can prove by mathematical induction. Okay, all right. So yes, so and the reason for doing this, so we have done it only for partitions. But if you have if you have a lattice S, and you look at all partitions of that, and you have a sequence Xn, and you have a sequence Yn, and then you define the multiplicative extensions, then that finite lattice will automatically have a Mobius function. So this function, it depends on what kind of ordering you have in the. So we have here we have the partitions and the reverse effacement ordering. So that particular ordering will give you one particular Mobius function. If your ordering is defined differently, some other partial order, then the Mobius function will change. That's all. Okay. But this one-to-one relationship is very nice. It's sort of universally available. So we are already given. So here M1, M2, M3 we have already seen. C1, C2, C3 you can solve like that. So here is the Mobius function really coming up here. So not everything will be positive. There will be some minus, there will be some plus, and some coefficients will be there. So these A, pi, sigma, this matrix entries are not that easy to write down. Okay. So now it's time for some examples. So it's just too abstract. So the Poisson probability measure is Pk equal to e power minus lambda power k by k factorial. It's very easy to see that if you sum them, it's going to be equal to 1. So this is a probability measure. Its moment generating function is easy to calculate because what the moment generating function is nothing but e power minus lambda times e power lambda kt lambda power k by k factorial, right? K equal to 0 to infinity. But that's, you can sum that, right? So if you sum that, you are going to get this. Okay. Now, if you're getting this, what is log of mt? That is e power, so log of mt is equal to e power, lambda times e power t minus 1, right? It's simple log here. And then when you expand this, all your coefficients are going to be lambda, right? Because this is nothing but lambda t power n by n factorial. Forget the minus there, yeah, okay. N equal to not 0, 1, right? So these are your coefficient Cn's. In other words, all cumulants are equal to lambda, constant, does not depend on n. Okay, and of course this is the only probability measure with this property. Because it will identify the moment, once you identify the moment generating function, like the Laplace transform, it identifies the measure. So here, if all the equivalents are lambda, then all the moments have to be, then the moment generating function has to be this, and hence it has to be a Poisson probability measure. There is no other choice. Okay. So using this, it can be checked that the nth moment of this Poisson probability measure. So what is the nth moment? Now here instead of this, I'll have k power n, right? Not easy to calculate. But because of this relationship that we have proved, this is nothing but mn lambda j s n j. Why? Because remember, what is mn? It's summation c pi. Every ck is equal to lambda. So c pi is going to be lambda power something. What is the something? Exactly the number of blocks that you have. So if you turn it around and you say that this is this block of size j, all partitions of block of size j, that is my number s and j, then it's going to be mn is equal to the polynomial in lambda. So this formula is not easy to find out, but because of what we have already proved now, this falls out easily. Okay? Okay. So in particular, if lambda is equal to 1, then you get the sum of all possible partitions of 1 to up to n, and that is nothing but the Bell number. So if you are teaching Poisson distribution to first year, second year undergraduate, you ask them to show this, they are not probably not going to be able to show this. They'll struggle, right? Okay, next example, the Gaussian measure. Again, because these two measures are familiar with almost every mathematician. So this is the Gaussian density. No one can show that the total integral is equal to 1, so this gives me a probability measure. Here, something very different happens. Alright. So let me define what I mean by a pair partition. A partition where every block is of size 2 will be called a pair partition. Means every block is of. So for example, if I have this set 1, 2, 3, 4, then this partition 1, 3 and 2, 4 is a pair partition. Okay, and this partition 1, 2, 3 and 4, this is not a pair partition. Okay, all right. So pair partitions can happen only if n is even, of course. All right. So I will denote the set of pair partitions of even number 1 to up to 2k as P2 of 2k. 2 means pair. Okay. It is also easy to find out the moment journey function of this density. Okay. So again, those who know Laplace transform will know that this is the Laplace transform of the Gaussian probability measure. Very easy to calculate that. You integrate the e to the power tx dx and you complete the square. You write that again as a Gaussian probability measure. Use the fact that Gaussian probability measure integrates to 1, and then because of the adjustment to make it a square, you will be left with this one. So this is the moment journey function of the Gaussian probability measure. Of course, if you take the log, it's a polynomial of order 2 in t square by 2. Okay, so log mt is now t square by 2, which means C2 is equal to 1 and there is no other term, or every other n for all n not equal to 2. So very unlike the Poisson probability measure, the Gaussian probability measure has only one cumulant which is non-zero, namely the second cumulant. Everything else is 0. Of course, if you think like a mathematician, your obvious question would be, this is a second degree polynomial. What about examples where I have a polynomial of finite degree? In other words, can I have, so by the way, let me call this CT, the cumulative journey function. Okay, so can I have CT, which is say, let's say A1t plus A2t square plus A3t cube? Is it possible? There is a very deep theorem which says that no other finite degree polynomial is possible. Only second degree polynomial is possible. Okay, this had only C2. It didn't have C1 because the mean is of this distribution is 0, right? It's a symmetric density. Okay, in general you can have A1t plus A2t square. So in this case, so A1, this is the mean of the distribution, and this is the variance of the distribution. That's why I defined the variance. In general, this is not possible. So there is a theorem which says there is no other finite degree polynomial which can serve as a cumulative journeying function of a probability distribution. It's absolutely non-trivial theorem to prove. Okay, so here to finish this slide, every partition contributes to the Poisson moment. Only pair partitions contribute to the Gaussian moment. Okay. Also, if you are trying to find out the moment of this function, you have to integrate x to the power 2n. It's not very hard to do. You substitute x square equal to something and use gamma integrals to do that. You can do that. But this formula will immediately tell you that this is what it is, because C2 is equal to 1. So when I try to find out the moment, again this formula. So this C pi will be 1, right? Because only C2 is equal to 1. So this C pi is going to be 1, but for partitions which are only pair partitions. So you end up counting the total number of pair partitions that you have. Okay? So you take the set 1 to up to 2n, and how many pair partitions of this set are there? That's an easy combinatorics problem. You can show that that number is nothing but this. So you have found out the moment. Without integration, you have found out the moment of the Gaussian distribution. Okay. Yeah, any questions? Right. Okay. So I'll introduce random variables. Many of you will know what is a random variable, but some mathematicians may not have seen this concept. It's just measurable functions, okay? It's a measurable functions defined on a space which has a measure, whose measure is a probability measure. That's all. That we call it a, instead of calling it a measurable function, we call it a random variable. Okay. So x is a real valued measurable function on some probability space. So probability space means that the measure is a probability measure. So its induced probability distribution P is the probability measure on R induced by this map. So every time I will call it a P, but P can be on the space omega AP, and then in the induced real line that can also, that's an induced probability measure, which is a push forward measure, but that also I will call it P. Okay, everything is P for me. So trivial example, consider a probability measure R, B, R, mu, and let X be the identity map, then X is a random variable with probability distribution mu. Okay, it's trivial example. Simplest example is where you have a coin which you toss, heads or tails, and you put probability half on H and half on T, so that's a probability measure, and define X, H is -1, you lose 1 rupee if it turns out head, and you gain 1 rupee if it turns out tail, then the X is a random variable. Then the induced probability measure is P minus 1 is equal to P1 equal to half. Okay. We write E of X power n for M and P. Alright? And in the above example, E of X is 0 and the variance of X is 1. Okay. So this is a one slide primer on random variables. Okay. So now let me give you this formula which I had mentioned in the beginning of the talk. So suppose x1, x2, xn is a measurable function on a probability space where whose induced measure on Rn is a Gaussian measure. Okay. And for simplicity, I have assumed that the Gaussian measure has mean 0. So its moment genetic function will be a quadratic function now, because there can be correlations between x1 and x2. So earlier it was only t square by 2, now you generalize that to t prime sigma t by 2, where sigma is a positive semi-definite matrix. It can be, some eigenvalues can be 0, it's allowed. For example, if I start with one Gaussian random variable x, and then I define x2 as x comma x, or y2 let's say, that's also by definition is a Gaussian measure. It will not have a density, but it's a Gaussian, because it will not have a density because its entire mass is on this diagonal. Okay, so it's not absolutely continuous with respect to the Lebesgue measure on R2. Okay. So anyway, this is how the moment genetic function looks like. So sigma can be singular. Okay. Even though I have said positive here. Then, so what we have done is we have defined moments and cumulants for one variable. You can actually do that for many variables also, which I have not done here for simplicity. Okay. So then, by using this, so now what will happen is, because of this t prime sigma 2, maybe I'll explain this a little bit. So earlier I had e to the tx p dx, right, because I had one measure. So now suppose I have a measure on R2. So then I'll have e to the power t1 x1 plus t2 x2 and p d x1 dx2. So this is a probability measure on R2 instead of R1. So okay. So now then, so this I will call as a moment genetic function, but now I have two variables to denote this moment genetic function. Okay. So now again you can have the cumulative genetic function by taking the log of this, and then you can expand that in like so t1 power k1, t2 power k2, and you have here the denominator, and let me save some time. So this is how the cumulative genetic function will look like. So c k1 k2. So depending on which power of the first variable, which part of how many parts of the first variable, how many parts of the second variable. Of course, this can be 0, so then you get the cumulant of the second variable. Or this can be 0, then you get the cumulant of the first variable. Okay. So now, because of this quadratic function, now you can see that only this c2 of only this C11, C20, C02, only these are non-zero, right? Because it's a quadratic function. So all other coefficients are zero. So this, by the way, is the covariance between x1 and x2. So in general, of course, if you have n variables, you have the covariance between xi and xj. So all possible ij, and so these are the sort of variables we get. So now, because of that, if n, again like in the previous case, if n is odd, then this expectation is going to be 0, because you cannot get equivalent with partition is odd sized. And since all equivalents of odd larger than 2 are 0, you will get E of x1, x2, xn as sum of product. Because as I said, if you get Ci here and Cj here, then that is nothing but expected value of xi times xj. Okay. So you will get these products. So ik, jk is a paired partition of 1 to up to 2n. 1 to up to n. N is assumed to be even. So this is a beautiful formula. Of course, in the Gaussian measure, you know that only because of the density and because of the moment-genetic function, only the values, the coefficients, the xi, xj, only those products are important. Everything else is irrelevant. But how it shows up in the formula is not that obvious. So this formula is not that obvious. Now it is because of the formulas that we have proved. So it tells you that any moment of the Gaussian variable can be calculated by looking at the product moments of only two paired, each pair, and then summing over all possible partitions. For example, if I have to calculate E of x1, E of x2, or x1 square, x2 square, I can do that. So I will think of this as partition 1, 2, 3, set 1, 2, 3, 4. These are related to x1 and these are related to x2. And then I'll look at all possible partitions and apply this formula. Okay, I can easily write that. I don't have to go through integrations. And also the beauty is that this will also work if all the xi's are equal. If all the xi's are equal, then you get x1 power n. And on this side, you will get E of x1 square only and all possible partitions. Immediately you get it.
So does this simplify if we have independence on x's?
Yes, if you have independence on x's, then this is 0, because I have assumed mean 0. So this is 0. Okay. If the x's are independent, this expectation is always 0. Whether it's even or odd, always 0. Which of course is also true from the fact that if you have independence, this is on this side you have the product expectation. By the way, for mathematicians, independence means the joint probability measure is the product of the marginal probability measures. That's what it means. Okay, so as I said, commonly this is referred to as Wick's formula after the work of Wick's 1950. Probably he won the Nobel Prize, but I'm not sure. So if you take xi equal to x for all I, we get back the earlier formula for the Gaussian moments. Okay. Now we'll switch gears. We have been talking about partitions and all possible partitions. Now I'll restrict my class. How much time do you have? Infinite, right? Raman is a man of infinity. So I will restrict myself to a smaller class of partitions, and something very interesting happens. So phi will be said to be crossing if this happens, which is not that easy to read, but if I draw a picture, which is about 1,000 words always, as they say, will make it really easy. So let me give you examples, okay? So if I have 1, 2, 3, 4, okay? Suppose my partition is 1, 2, and then 3, 4, okay? So I join these points because they are the same block of the partition, and I join these points. And then you can see that these two arcs or segments, they do not cross each other. Then it's a non-crossing partition. On the other hand, if I have 1, 2, 3, 4, and I have my partition is 1, 3, and 2, 4, then it's a crossing partition. Okay, very easy. So that is what this thing means. So if pi is not crossing, then it's called non-crossing. And the set of all non-crossing partitions I will denote by NCN. First interesting thing is that this NCN Of course, it inherits the ordering that we already defined for all partitions. That ordering is still there, but it's still a lattice, which means you can find the maximum of. So if I give you two partitions, you can find the smallest maximum of the of these two partitions and the largest infimum of these two partitions. Then it's called a lattice. Right? So this NCN is a lattice. It's a finite lattice. So it will immediately have its Mobius function. Okay. All right. So for example, NCN is PA for n equal to 1, 2, 3. So if I have 1, 2, 3, no matter how you partition, this is 1, this is 2, this is 3. No matter how you partition, you will not be crossing. So up to n equal to 3, things are very easy. But it's not so. As we have seen in the case 4. So how many non-crossing partitions are there for this case? 1, 2 and 3, 4 is one partition, and you can check that 1, 4 and 2, 3 is another one. And these are the only two non-crossing partitions of 1, 2 up to 4. But there are plenty of other partitions of 1, 2 up to 4. Okay. And 1n is in NCN and 0n is also in NCN. And as I mentioned, it's a lattice. So here is the example. So these are the only two non-crossing partitions of 1 to 4, and this is not a non-crossing partition. Okay, example Z7. So pi 1, this is a non-crossing partition, this is a crossing partition. So as I already drew a picture, so if you look at these two partitions, this partition is non-crossing, this partition is crossing. The partition means here 1, 4, 7 is one block. Okay, so Catalan numbers. I'm absolutely sure all of you know what Catalan numbers are. But you may have had different definitions of Catalan numbers. There are like more than 100 ways of defining Catalan numbers depending on the context. So they are very important, useful numbers. So these numbers are the Catalan numbers. They arise as counts for many different things or objects in mathematics. Okay. So here is a wonderful result. I am not going to prove it. Remember we talked about pair partitions, right? So we can do that for non-crossing partitions also. So NC2 2n will denote all the non-crossing pair partitions of 1 to up to 2n. There is at least one, 1, 2, 3, 4, 5, 6 and so on. That's a non-crossing partition. Facts. This NCN is the set of all non-crossing partitions of 1 to up to n. NC2 2n is the set of all non-crossing paired partitions of 1 to up to 2n. And these are in bijection. Number 1. Number 2, the total number of non-crossing partitions is equal to, because they are bijection, they are the same, and that is nothing but the Catalan number of order n. This I will not prove, okay? It's not very, this needs a little bit of work, this is not very hard to do. Okay. Alright. So now I define a new probability measure. I am short circuiting things. In random matrix theory, this semicircle distribution or semicircle probability measure is a very important place for many other reasons which I will not go into here. I will just go straight and define this as follows. So this is the semicircle probability density. The important thing to note is that this density is in this interval -2 to +2. Okay, so it looks like a semicircle, but it's not quite a semicircle. That's why it's called that name is stuck from physics. They call it the semicircle probability measure. Its moment sequence, very interestingly, not very hard to find out. You take x power k times this and dx. You substitute something, do some substitution. It becomes a beta integral. You solve the beta integral. You get the value. Turns out that hth moment of this measure is Cn if h is equal to 2n. So the 2nth moment of this measure is the Catalan number of order n, and all other moments are 0 because it's a symmetric distribution. So if you have an odd function, it will be 0. Okay. Now it's time to look back at the Gaussian measure that we have seen. For the Gaussian measure, the 2kth moment was P2 of 2k. So you look at all pair partitions of 1 to 2k, the total number is the Gaussian moment. For the semicircle, 2kth moment is the total number of pair partitions, but now of the non-crossing partitions. Okay. So that is a very important and interesting relationship. For the whatever happens for the Gaussian moment in terms of all partitions, same thing happens for the semicircle law in terms of the non-crossing pair partitions. And this distribution is also known as the free Gaussian law for reasons which I cannot go here. So this freeness has to do with some notion of independence that is there, and this freeness also comes out from free groups and free algebras in maths. So everything is in this world is connected. The relation between the two measures goes much deeper. As I said, I will not go into that. That will need another lecture. Okay. Now, I will connect this with random matrices a little bit. So I am almost at the end of my talk. So NC22N, a closer look. Suppose V1, V2 and other blocks of pi. Here we have arranged the blocks in increasing order of the smallest element within each block, and we write the smallest element first. For example, if this is the partition, then I write 1 first and then 3, then 1 first and then 2 are the only two non-crossing pairs. Similarly, 1, so this is a non-crossing partition of 1 to up to 6, so 1 and then 2 and then 4, then 1 and then 3, and so that's the ordering that I will write them in. 2 of the 5 non-crossing partitions of Z6. Okay. Now, let us assign one letter in alphabetic order to all elements of each block. Okay. So, it will be clear why I am doing that. So, 1, 6, 2, 3, 4, 5, this was a non-crossing partition. So, I will represent them by a string of letters. So, each letter, because each block is of size 2, each letter will be repeated 2 times, precisely 2 times. And the way I will write this is in order. So, 1 and 6. So, 1 is A, and 6 is also A. And then 2 is a new letter because it's a new block. And 2 and then 3 is same, so 2 and 3. So, elements of the same block will get the same letter, but they'll get a new letter every time I move to the right. Okay, 4, 5 will be C, C. Alright, the idea is clear. So, which words arise in this way? It's easy to see that each such word has a double letter. Okay, at least one double letter has to be there, because the last time you have, so has a double letter, the last two letter is always a double letter. And once you remove a double letter, for example here, this is the last letter, this is, if I remove it, I'll get A, B, B, A, then again this is the last double letter, I remove it, then I get A, A. So everything is gone, okay? So if this successive removal is done, nothing will be left. That's how you can also define it. So this yields a one-to-one correspondence between the non-crossing pair partitions and words which are written like this. Okay, very good. So now, let me introduce a little bit of random matrix, only scratching the surface. So what is a Wigner matrix? Wigner is again a physicist, and this was defined by Wigner, who also was a Nobel Prize winner in 1955. So this is how we defined it. So for now, the Wigner matrix is a matrix. It's a square matrix. It's a symmetric matrix. So this side is equal to that side, and every entry xij. So all these entries are independent of each other. And to standardize things, you assume that all of them have mean 0 and variance 1. Okay? Alright. Now the spectral measure of any matrix, you take the...
So we have
5 minutes. I will finish in 5 minutes. Okay. With a grace of 10 minutes. Okay. So... But I lost 10 minutes in the beginning, you remember?
the talk was of 45 minutes, 50 minutes question.
I was not through that. Did anybody hear? Okay. So this is the spectral distribution. So you look at the eigenvalues and you put probability 1 over n at each of these values. Okay. So this is a random probability measure because the eigenvalues are random variables. They are measurable functions of the entries themselves. Okay, so now the general question in random matrix series is to study this eigenvalue distribution as n goes to infinity. So I'll speed up a little bit. Okay. So the Wigner matrix is very interesting. What happens to the Wigner matrix is, if all it's a symmetric matrix, so all entries have independent identically distributed entries, meaning they have the same probability law, and E of x squared equal to 1 to make it standard. And then for simplicity, you can assume that each entry you put a plus or minus 1 by tossing a coin. Okay, you take one coin, you flip it that many times, every time you get a head or a tail, you put a plus or a minus 1 depending on what it is. And then you scale this matrix by 1 over square root of n, and the very fundamental theorem in random matrix theory is that this measure that you get out of doing this, they converge to a semicircle law, the free Gaussian law. Okay. All right. So if you want to quote one theorem in random matrix theory, that this is the one. Wigner, of course, did not prove it in this generality, but he was a much more specific case, but it's known as Wigner's law. Semicircle law is also known as Wigner's theorem or Wigner's law. Okay, now I want to generalize this. How do I generalize this? So this was part of a work with my PhD student. So our question was the following. Well, you got the semicircle law. Are other laws possible? Of course, not possible if all the entries are I.I.T, but if I can tweak the things a little bit. So remember I talked about tossing a coin, plus or minus 1 with probability half each. So suppose at the nth stage, I put plus or minus 1, but I have to scale them to make it mean 0. But probability of, let's say, head, probability of 1 is Pn, and probability of minus 1 is 1 minus Pn. Okay, suppose. And then suppose that n times Pn converges to lambda. So those who work in probability will know that this is the Poisson regime. Here what happens is the binomial distribution will converge to the Poisson distribution. Okay. So here what it means that there will be a lot more ones than minus ones. Lot more minus ones if Pn is, because Pn is going to 0, right? If Pn goes to lambda, this Pn will go to 0. Okay. So there are a lot of minus ones and much less ones. Okay. Then what happens to the eigenvalue distribution? It so turns out that this eigenvalue distribution also converges. Not that easy to prove, but one can prove that. Okay. And that is related to now the semicircle law does not remain the limit of this measure anymore, but it's a much more complicated distribution. And that complicated distribution can be explained through this. So a partition 1 to 2k is a special symmetric partition. If the last block is a union of even sized sets of consecutive integers, and maybe it's a little bit hard to see what this definition is. Maybe I'll just give you an example. So for example, this will be an element of SS2k. So there is a 1 block, 2 blocks here. But so what I've done is I've moved away from pair partitions. But some of the other structures are remaining. For example, this can be also there. Okay, all such possibilities are there. Okay, so so happens that each of these blocks is going to contribute some number. Earlier each pair partition was contributing 1. Now each of these is going to contribute some power of lambda. Okay, depending on how many A's and how many B's you have. Okay, so let me skip that because I've been warned. So SS2k, now there are big differences. This SS2k, unlike NCK, is not a lattice anymore. So you cannot use any of that theory. For example, so there's an example, let's not worry about that. It happens so that if you look at this set SS2k, they define a probability measure. In other words, you can get a probability measure whose 2kth moment is equal to this, and whose other moments are equal to 0. And this measure, unlike the previous measure, which was on -2 to +2, this has unbounded support. So a lot of things have gone differently. Here's an open question. It's not a trivial question, it's a very difficult question. There is no known formula for the recursion or otherwise for SS2k. Like NC22k we saw, well, there's a Cattle number. So nobody knows what this number is. Dropping specific types of letters or blocks from SS2k do not lead to recursion equations. That's what the difficult problem. NCK and NC22k, you can prove those formulas by induction. Here it will not work. Okay, and SSB2k are all partitions of words in SS2k which have exactly B blocks. Earlier, with it had only 2n size, it had exactly n blocks because everything was a pair partition. But not everything is a pair partition now. Okay, so then this is what happens. So suppose Wn is an n cross n symmetric matrix, as I was saying, Pn and 1 minus Pn, then the spectrum of Wn by root n converges weakly to this measure with these as the moments. These numbers are not known, and that's where things stand. But they do look very much like the Poisson moment formula that I gave you earlier. Okay. Okay. So maybe I'll skip this. This is related to counting the number of colored rooted trees. Maybe I will I will skip that because of time. Okay, all right. Thank you very much.
So, when we define this random matrix, so it's a matrix whose entries are random variable. So, in general, the standard notion of matrices are known as a linear transformation. So, can we have similar sort of notion for this random matrices also? Like, can we see it as a linear
Operator, as an operator. Yes, you can do that, and it has been done. And yeah, you can do that. But in some cases, things are easy to analyze. I've given you only one example of random matrix here today. Or
Like,
actually two.
I was thinking that if we fix a omega,
Yes.
we'll get a real matrix,
Yes.
and that will be a linear transformation from
Yes.
some vector space to
Right,
another.
right.
But since it's a random matrix,
But
so
yeah, okay. So his question is the following. So if I have x1, x2, if I have this Wigner matrix, then I can think of this as a function of omega, where omega is the basic space for where this. So can I study this? And the answer is no. So and that is why there are many different ways of saying what I mean by the. So this operator, for example, will not make sense in the usual operator theory notions. No operator theory notions will make sense when n goes to infinity. Okay, but as we have seen, I was probably not very careful in stating the theorem precisely. So one can show that if you look at the eigenvalue distribution, so this is random probability measure. So let me call that mu n. But because it depends on omega, let me introduce omega. So for almost every omega, this measure converges to the semicircle law. Almost every omega. Okay, that needs some work.
no, like I wanted to ask that. Now suppose M is a matrix,
Yes.
so it will be linear transformation from some vector space V to.
Yes.
Now since in this case we have this random matrix.
Yes.
And for each omega, it will be a real matrix, and that
Yes.
will be some linear transformation.
Yes.
Now I want to, if I want to see it as a whole function, so it will be a function from some vector space cos omega to some
Yeah.
vector space.
Yeah.
So when we fix omega, it will be a linear transformation.
Sure.
So I just wanted to know what kind of map we will have if we fix this element
The
from V,
problem-
not omega.
Yes, I have understood your question. The problem is defining that vector space that you want. So as n becomes large and large, there are different vector spaces, and there is no one way of there is no common ground on which you can define all these matrices and one vector space. See, this vector space now, as n goes to infinity, this vector space is infinite dimensional, right?
Yeah.
Yeah, and that infinite dimensional vector spaces, usually you have this, for example, Topli's operators. You have to assume some conditions of on the entries. For example, the vectors in L2, like the L2 Hilbert space. Okay, so that will not work in this case because observations are IID. So because observations are IID, this summation xij square, that will be infinite.
Yeah.
Okay, so that is the problem with the vectors. But there are results on. So you can consider the eigenvalues or eigenvectors of this matrix. So there are some results on the eigenvectors. So they are random vectors of order of dimension n as n increases. So you can do something with them.
Okay.
Yeah. Thanks. Yeah.
So, any other question? I have one.
Yes.
Does this have application in graph theory? I mean, some application of this sort.
Yes. The Wigner matrix with this, instead of plus minus 1, you can put 1, 0, then it becomes the heterostratic graph, the complete heterostratic graph. So you can, adjust the matrix of that.
Is there any work that some people have done that?
Yeah, I mean, you know that this is a special case. The adjacency matrix will have zeros and ones. So if there is xij is either 1 or 0, then it becomes the adjacency matrix of the complete heterostratic graph. So Yeah, so you can have other models though. I mean, instead of all plus or minus ones, you can have other structures in the matrix, and there are some results on that. So yes, the special case of the Wigner matrix is nothing but the adversary random graph, complete graph.
Any other question?
So any other practical application we can think of that this particular theorem is
Not particularly this one, but see, you should think of this as the central limit theorem for random matrices. Like when the observations x1, x2, xn are right, you know the central limit theorem, right? So x1, x2, xn are ID, you add them up and you divide by square root of n, then it converges to the Gaussian distribution. So this is a theorem like that. That itself may not be interesting, but what will be interesting and has been put to use is that if you build other models on the basis of this Wigner matrix, are more complicated models, then they have applications in wireless communication, in statistics, in probability, many other areas. Thank you, sir. So, but this is a very simple, basic thing, so it's not.
Okay,
So by the way, let me extend that answer. So for example, I know from a friend of mine who works in this wireless communication, this 5G network system, that was based on the basic maths that was there was this random matrix theory. So they use the random matrix theory to develop 5G networks. Thank you again for coming to my talk.
Thank you, sir, for moderating the first session. I request you, sir, to felicitate Professor Arup Bose with a memento which depicts the local art and craft of Chhattisgarh. Thank you, sir. There is an arrangement of tea outside, so I request everyone to proceed for the tea to designated area, and we will resume again for our next stop at 12 p.m. But it's already 12, so 12:30, 12:15, 12:15 p.m.
হ্যালো, না আমি শুনতে পাচ্ছি না। হ্যালো, হ্যালো, না আমি হ্যালো, না এখানে শুনতে পাচ্ছি না। হ্যাঁ, না ভলিউম বাড়ানো আছে। হ্যাঁ, হ্যালো, হ্যাঁ, হ্যালো, হ্যাঁ বলুন। হ্যাঁ, হ্যালো, হ্যাঁ এবার শুনতে পাচ্ছি এখানে। ঠিক আছে, ওকে, আমি শুনতে পাচ্ছি। ওকে, yeah, now it's okay. So I'll start sharing my slides then. Yeah.
Like to request the convener of today's event, Dr. Rajkumar Mistry.
Good afternoon, everyone. So now we have the speaker, Professor Munshi. So welcome, sir. It's my privilege and honor to introduce you, sir. So Professor Munshi is a distinguished Indian mathematician who specializes in number theory. He is known for his contribution to the subconvexity problem for automorphic L functions. He completed his PhD in 2006 from Princeton University under the guidance of renowned mathematician Andrew Wiles. After completing his doctoral studies, he served as a Hill Assistant Professor at Rutgers University, where he worked alongside Henry Ivanuel, a prominent figure in analytic number theory. Professor Munshi was also a member of the Institute for Advanced Study in Princeton during 2009 and 2010. His outstanding contribution to mathematics have earned him numerous accolades. In 2015, he was awarded the prestigious Shanti Swarup Bhatnagar Award in the Mathematical Sciences by the Council of Scientific and Industrial Research, which is considered India's highest recognition in science and technology. Additionally, he received the Infosys Prize 2017 in Mathematical Sciences and the ICTP Ramanujan Prize in Statistics and Mathematics Unit at the Indian Statistical Institute, Kolkata. He is also a fellow of both the Indian Academy of Sciences and the Indian National Science Academy, reflecting his prominent status in the scientific community. In addition, he serves in the editorial board of the Journal of Ramanujan Mathematical Society and the Hardy Ramanujan Journal. This is a brief introduction, so list is long, so if I miss something, so please forgive me. So now I invite Professor Munshi for the talk. Welcome, sir.
Thank you. Thank you for the introduction, and thank you for the kind invitation. It's always a pleasure to give a talk on the on this occasion of the National Mathematics Day. So we celebrate the birthday of Ramanujan. So let me just begin by saying that there is a lot of confusion about what Ramanujan actually did to mathematics and what is his contribution to modern mathematics. The thing is that the confusion is there because when you look at Ramanujan's work, especially his notebooks and the letters he sent to Hardy, those are just filled with formulas. and he doesn't give any real proof of the things there. Though there are some proofs that appeared in some of his papers with Hardy, but in his notebook he never wrote any proof of the formulas. Sometimes he gave some ideas how to prove these things. So that's the main reason of confusion. And the other thing is that these formulas are really will appear foreign to most of us, because we're like 100 years after Ramanujan, and the mathematics that he was doing back then, it's kind of an old type of mathematics now. So that's the reason. Some people ask why, so they mentioned this story of Hardy and Ramanujan, the taxi cab number 1729, and whether they wonder whether that made Ramanujan famous. So the story goes that Ramanujan was in a hospital, sick with something, and Hardy came to visit him, and he said that he came by a taxi whose number was 1729, and he really thought it's a very bad number, so probably there's something bad going to happen. So Ramanujan quickly replied that 1729 is a very interesting number because it can be written as a sum of two cubes in two different ways. Okay, so that's kind of surprised Hardy, and people, many people still think that it's a great thing that Ramanujan realized that 1729 is a sum of two cubes, the smallest number that can be written as a sum of two cubes in two different ways. But the surprising part of the story is not that Ramanujan came up with this reply. The surprise is that Hardy missed it. Okay, so 1729 is something, not 1729, but 1728 is the number which appears everywhere in the theory of modular forms, and it clearly shows that Ramanujan was really in the theory of modular forms, whereas Hardy was not that much in it. Okay, and the theory of modular forms is right now is all of number theory, and so even like 100 years back, Ramanujan was really doing modular forms when he said this thing. Yeah, I was looking at the poster, and you have written this nice formula of 1 by pi, 2 root 2 divided by some number, and the series, and also there is a poster where you mentioned this quote of Ramanujan that something is interesting because when it reflects a thought of God. Okay, so what is the thought of God that that Ramanujan was mentioning in this formula? So this formula is it's a typical example of type of mathematics that Ramanujan used to do back then. And right now, people looking at that formula would say that, okay, what does it give? It doesn't give anything. It just gives a way of writing down pi in an infinite series. And maybe that can be used to evaluate pi precisely by taking some terms from the series. Okay? But as Ramanujan says, that it doesn't make much sense unless you know the thought of God behind it. And what do you mean by the thought of God? Okay, so Ramanujan, I think, as far as I realize now, that what he meant is the mathematics that's behind this expression. Okay, the theory, the theory of modular forms. Okay, and Ramanujan realized that probably as a thought of God. Okay, so yeah, but maybe it might have meant something much more deeper, which is probably just beyond me. But anyway, so I've been given talks on this National Mathematics Day for a few years now, and it's always been making this talk quite technical. I've spoken about circle method and spoken about modular forms and the contribution of Ramanujan to those method, the circle method and modular forms. But it's always, it becomes very, very technical. So today I'll just try to start with something very basic. So this is a sphere and in 3 dimension. Okay, it has a simple equation, x squared plus y squared plus z squared equals to 1. Okay, it's just a ball of radius 1 in 3 dimension. What we're going to do is we are going to look at larger spheres. So here is another sphere of radius square root of r, x squared plus y squared plus z squared equals to r, right? So there, and the unit sphere sits right inside it. And we can define a map, a geometric map, from the bigger sphere to the smaller sphere, just by joining a point, take a point on the bigger sphere, join it to the origin, the the 0, 0, 0 point, and that should intersect the unit sphere at some point. Here, the point I'm taking on the bigger sphere is P. I'm joining it to this unit with the origin, and this intersects the smaller sphere at Q. So it gives a projection of the bigger sphere onto the unit sphere, and that I'm going to denote by pi r. Okay? It's just a simple radial projection. It's geometry. So if you take the point x, y, z, then pi r of x, y, z is just dividing it by square root of r, x by square root of r, y by square root of r, z by square root of r. Those are the coordinates of Q, once you know the coordinates of P. Okay, and so this is the geometry part, the very basic school geometry. Now comes the arithmetic. Okay, so I'm going to throw in some arithmetic here. Okay, so I'm not just going to look at any random sphere, but we're going to look at spheres which have the equations given by x squared plus y squared plus z squared equals to n. So where n is going to be a natural number, 1, 2, 3. So if n is 1, then it's just the unit sphere. Then we are taking larger and larger sphere, S2, S3, okay, bigger and bigger. And then we're interested in the arithmetic points on those spheres. So we're interested in what are called the lattice points. So we're looking at x, y, z, all of them integers, such that their sums, sum of the squares add up to n. Okay, x squared plus z squared, y squared plus z squared equals to n. So this is just the set of lattices, lattice points zq in 3D, divided intersection Sn, right? So this set I'm going to denote by Rn. Okay, here is an example. If you want to look at R1, it's very easy to write down the solution of the equation x squared plus y squared plus z squared equals to 1, where with x, y, z all integers. They are just on the axis, plus minus 1, 0, 0, 0 plus minus 1, 0, and this one. And you can also list down the points on S2, lattice points on S2, lattice point on S3. It is a very easy exercise, and you'll see some sort of symmetry. Of course, you can permute x, y, and z in any way you want. You still get a lattice point on the sphere. You can change the sign of x, y, and z, either any of them or all of them. It will still give you a point. So there are a lot of symmetry, okay? And that's why you see all these plus minus signs. You see that, the change of positions. Okay, and they are all giving you new lattice points on the sphere. So as you go on, you get points, but at one point, say R7, if you're looking at lattice points on the sphere whose radius is square root of 7, then there are no points. Okay, it draws a blank. Okay, and it's very easy to see why R7 is the empty set, because if you look at this equation, x squared plus y squared plus z squared equals to 7, and if you assume that there are integer solutions to this, x, y, z are integers, then you can reduce this equation modulo 8. Okay, you can look at the remainder of x when divided by 8, remainder of y when divided by 8, or z divided by 8. That's just modular arithmetic. That is just the map from going from z to z modulo 8z, right? So if there are integer solution, then there should be solution of this in this ring, z modulo 8z, right? And so now we look at the squares modulo 8, and we quickly realize that there are only 3 squares modulo 8, 0, 1, and 4. And the problem is to see whether we can pick 3 of them, we can, with repetition, such that they add up to 7, modulo 8 or not, okay? And these are the only ways you can pick 3 squares modulo 8. And you see that you can get 0 modulo 8, 1 modulo 8, 2 modulo 8, 3 modulo 8, 4 modulo 8, 5 modulo 8, 6 modulo 8, but never 7 modulo 8. So there is a local constraint at 8. This is what is called a local constraint. If you have integer solutions to some polynomial equation, then modulo every integer, you should have solution. And if you don't have solution modulo some integer, then that is the local constraint to having equation. Okay, so if you don't have modulo some integer solution, you don't have solution for over integers. Okay, and yeah, so we can conclude from here is that no number which has remainder 7 modulo 8 can be written as sum of 3 squares. Okay, so we need to knock them out from our consideration. And in fact, there is this famous theorem of Legendre. There is a caricature of Legendre. So apparently this is the only picture of Legendre available to us. His famous theorem here says that, proved in 1797, says that if an integer is not of this form, okay, it is not, so it's 4 is x squared. So 4 to the power k times 8l minus 1. For example, 7 is of this form, right? You can take k equals to 0, l equals to 1, that will give 7. You can get 13 of this form and so on. Yeah, we can get 15 of this form and so on. And these numbers can never be written as sum of 3 squares. So Rn is empty for these numbers. But if n is not of this form, then Rn, if Rn is of this form, then Rn is empty. If Rn is not of this form, then Rn is not empty, right? So that's a famous theorem for Legendre, which integers can be written as sum of 3 squares. So we know that with spheres, Sn will have lattice points, right? Okay, so let me take a short detour over here and mention something which is related to Ramanujan. Okay, so Ramanujan generalized this. He generalized the question actually. So he asked, okay, so instead of looking at sum of 3 squares, let's look at a more general ternary quadratic form, okay, with integer coefficient aij. So here x1, x2, x3 are the 3 variables instead of x, y, and z. And you have a ternary quadratic form. Ternary means there are 3 variables, quadratic because the degree is 2. And you are interested in answering which integers are represented by this form. And curiously, no general answer is known for this, okay? And Ramanujan, in a footnote in one of his papers from 1916, he mentions this quadratic form x squared plus y squared plus 10 times z squared. So you're just taking the sum of 3 squares, but the last square is multiplied by 10. And he wanted to see which integers can be written in this way. And he could prove that that even numbers of this form, 4 to the power k, 16l plus 6, cannot be represented. This is again coming from local constraint. So the even numbers which are of this form cannot be represented as x squared plus y squared plus 10z squared. And then he wrote down a curious list of odd numbers. Okay, 3, 7, 21, 31, 33, 43, etc. And he said it's not a simple list, so there is no simple pattern there. He ends this list with a dot, dot, dot. Doesn't say whether it goes up to infinity, or there are infinitely many odd numbers here, or there are only finite numbers. And he said that these are the integers, odd integers, which cannot be written as x squared plus 10 squared plus y squared plus 10z squared. All right? And it's still unknown, right? What is known is if you assume a very strong conjecture, it's called the generalized Riemann hypothesis, then the odd integers which are listed by Ramanujan up to 307, 391, up to this, and 2 more odd numbers, 679, 2719. So if Ramanujan had gone a little bit more, except this odd integers, all other odd integers can be represented as x squared plus y squared plus 10 squared. So say that the difference here is that Legendre gave a complete solution for representability as sum of 3 square. And starting from there, Ramanujan came up with an example where the pattern is totally different. Okay, they're even in numbers which cannot be represented in this form have a nice pattern. But if you look at the set of odd numbers which cannot be represented, it's only finite, and there is no set pattern over here. Okay, so that's an example of the genius of Ramanujan. All right. Okay, so now let's come back from the detour. But yeah, so I want to, before going any further, I just want to mention this this theorem of Lagrange. Okay, so Lagrange in 1770, so this is a picture of Lagrange. He proved that any integer, any positive integer, can be written as sum of 4 squares, right? And this is kind of an easy theorem to prove. Right now, after 250 years, we can say it's quite easy. But one should mention that Great Weller tried to prove it for 40 years without much success. So it was not that easy back then, right? But you can, if you assume Legendre's 3 square theorem, then you can quickly give a proof of Lagrange's 4 square theorem, right? So you look at any integer n. So I assume that Legendre's 3 square theorem, I want to prove that any integer n can be written as sum of 4 square. So any integer n can be written as 4 to the power k times m, right? So I'm taking out the highest power of 4 that is inside n, and m is what is left with. So m is either 1, 2, or 1, 2, 3 modulo 4. It cannot be divisible by 4 because I've taken out all the powers of 4, right? So if m can be written as sum of 4 square, so can be n, because 4 is already a square, right? So we want to show that any integer which is congruent to 1, 2, 3 modulo 4 can be written as any positive integer can be written as a sum of 4 squares. Now, if m is congruent to 1 or 2, then you can use Legendre's theorem, which says that in this case, these numbers can be written as sum of 3 squares, and because if m is congruent to 1 or 2, then it's not congruent to 7 modulo 8. So we have the answer that is written as sum of 3 squares, so it can be written as sum of 4 square, the fourth square being 0 square. On the other hand, if m is congruent to 3 modulo 4, which includes the example 7, then you can just look at m minus 1, because m minus 1 is then congruent to 2 modulo 4. So m minus 1 can be written as sum of 3 square. So if m can be written as sum of 3 square plus 1, and 1 is a square, so m can be written as sum of 4 square. So Legendre's theorem implies that any positive integer can be written as sum of 4 square. Okay, now we want to go back to the main problem that we wanted to address. Okay, we want to relate, we have this points on spheres, we have that projection map, and so that was the geometry, this is the arithmetic. We want to mix them and come up with an interesting problem. Okay, so so Rn was that set of lattice points on the sphere Sn. And we know when it's empty, when it's non-empty, that's Legendre's theorem. Siegel actually proved a much stronger theorem. Siegel proved that if n is not of this form, okay, if n can be represented as sum of 3 square, then the number of representation is quite large, okay? It's like n to the power half, right? So there are quite a few ways of writing n as sum of 3 squares, right? And here's a heuristic. This is just assuming that things are equidistributed, because if you can write x as n as sum of 3 square, then x, y, z, all of them should be less than or equal to root n. Then you look at the collection of all x, y, z with x, y, z less than root n, and then you'll see that you have n to the power 3 by 2 many such triplets. And for each triplet, you have the sum of 3 squares, and this sum of 3 square taking values in the range from 0 to 3n. So if you assume that whatever is represented equally often, then the number of ways any integer which can be represented as sum of 3 square can be represented in the number of points we have divided by the range. Okay, so it is n to the power 3 by 2 by n, so it's root n. Okay, so that's the heuristic. That's what we expect, that if n can represent a sum of 3 squares, then the number of representation is like n to the power half. So you can forget this epsilon. This epsilon means that it's not really n to the power half, but you can really go very, very near to n to the power half, right? Okay, so yeah, so now we are back to that projection map pi n. So we are now taking these lattice points on that big sphere Sn, and we are projecting it down to the unit sphere S1. So that's my set sigma n. And if typically, if n is represented, then the sigma n is of size, number of points there is like n to the power 1/2. So as n goes to infinity, we are getting more and more points on the unit sphere, okay? And the problem we're interested in is in the spatial distribution of this arithmetic data. So here is it's picture of what happens. So if you take this n to be like a 3 or 4 digit number, so this is, you have some points over here. You can see how these things are getting distributed. So if you take n larger, you get more points. And even more larger, you get much more points like this, okay? And you ask how those points getting distributed, whether there are, certain direction where you expect more points or certain directions where you expect less points, right? Not so. That's a conjecture of Linnick. So Linnick conjectured that these points are getting equidistributed on the unit sphere. Okay, so what does it mean? It means that if you take a subset, a measurable subset of the unit sphere, okay, then if you count the number of this point sigma n falling in that region, divided by the total number of points on this on Rn or sigma n, that's same, then this should converge to the integral of mu, which is the probability measure. So this is just the area. Okay, if you assume that the area of the sphere, unit sphere, is 1, if you normalize, then it is just converging to the area of that set omega that you picked. Okay, so that's the meaning of equidistribution. So the number of points asymptotically will depend upon the size of the set that you pick, but not on the orientation where you're speaking, or the shape of the set that you're picking. Okay. In other words, if you want to show this is equivalent to showing that, so if you take any measurable function f on the unit sphere, okay, and you look at this average, so fv, v is in that set sigma n, and divide by Rn. So this is the average of that function f, then this should converge to the integral of the function. Okay, so it's like the Riemann sum converging to the integral. So that is an equivalent statement. Okay, so this is, so if you want to show that sigma n is getting equidistributed, it's same thing as showing that for any measurable function, this limit holds. Okay, there is a standard reduction, of course, that you don't have to really show this for every measurable function. What you can do is you can just restrict to a collection of functions whose vector space span is dense in the set of measurable function. And that should be enough, because you can, if this thing holds for f and g, then it should also hold for f plus g. Okay, and if you have a sequence of function, and if this holds for all the elements in the sequence, then it also holds for the limit. You have to use some convergence thing from measure theory. And so you don't have to really look at all measurable function. We can just restrict ourselves to certain special functions. And those special functions, when you're looking at sphere, are called spherical functions. Okay, spherical functions are just homogeneous polynomials. So these are polynomials in the 3 variables x, y, z, which satisfies this equation. So if you differentiate with twice with respect to x, y, and z and add them up, it should be 0. Okay, and this collection of spherical functions, they span the space of measurable functions. So if you just take the vector space span and the closure of that will give you all measurable function. All right. So of course, if you take the constant function, then it's a spherical function. That's the easiest one. But you can, so since these are homogeneous polynomials, basically, there is a degree. Okay, so for every degree you have spherical function. So suppose P is of degree K, then you can easily show that its integral over the whole sphere is 0. So if you want to prove this thing over here, say this integral is 0, so we have to show that this sum is actually going to 0, right? So this is that sum on the left-hand side. And since this is a homogeneous polynomial, I can take out root n to the power k, and that gives me n to the power k by 2 by Rn, and this sum. Okay, so this is we are looking at the value of the homogeneous polynomial for every point x on Rn. Right? The point x is on Rn, x by root n is on sigma n. Huh? Right. So we want to show that this goes to 0. Right. We know that size of Rn is like n to the power 1/2. So we have this sum divided by n to the power k plus 1 2. So if I can show that this sum, which I'm going to denote by Rpn, okay, the sum over this spherical function over all lattice points Rn, then if I can show that this is bounded by n to the power k plus 1 by 2 minus some delta, so k plus 1 by 2 is kind of a trivial bound for this because the number of points on Rn is root n, and since p is homogeneous of degree k, so x is like root n, so it gives you n to the power k by 2 and root n, so n to the power k plus 1 by 2. That's kind of a trivial bound for this. But if you can have a saving over here, because you expect some cancellation here, because it's a spherical function, so there will be some terms with negative sign, some terms with positive sign. So at the end, they should just cancel out, and so the leading term should just cancel out, and it should be just left to the error term. But it's not that easy to prove. So that's our target. We want to show that the points on the sphere are getting equidistributed, the lattice points on the sphere are getting equidistributed. We have to show that for any spherical function of degree, positive degree, that this is bounded by n to the power k plus 1 by 2 minus delta. So there's a non-trivial bound. That's what we want to prove. All right. So I hope that at least the statement of the problem is clear. And now I just, so if you have any question, you can ask me. If you don't ask me in so I'm going to assume you're all fine with it. Right, okay. All right, so now, yeah, what Letic did is he used ergodic theory to study this problem. He actually came up with a solution. He actually showed that the lattice points on the sphere get equidistributed. But we want to take a totally different view. It's an analytic number theoretic way of proving equidistribution. The advantage of this approach is that it will not only give you an equidistribution, but it will give you a rate of equidistribution. How fast is the equidistribution occurring on the sphere? Okay, and all right, so this is also a Ramanujan style of doing mathematics. So if you want to study, yeah, so we want to study this sequence Rpn. We want to get bounds for this sequence Rpn. So what Ramanujan does is, so if you look at his paper on partition function, again, there he wanted to study the asymptotic of the partition function. So what he did is looked at the corresponding generating function and came up with analytic properties of the generating function. That's what we're going to do over here. So we look at the corresponding generating function. So Rpn e to the power 2 pi I n z, right? So this can also be written as Rpn q to the power n. This is a more standard way of writing a generating function. But the variable q we are going to take as e to the power 2 pi I z, okay? Where z will be a point on the upper half plane. So z will be a complex number x plus iy, whose imaginary part is positive. All right, so these are like holomorphic functions on the upper half plane. And Rpn is a Fourier coefficient of that. And or if you look at this one, Rpn q to the power n, you can think of it as a holomorphic function on the punctured unit disk, okay? And then if you want to estimate Rpn, you can use Cauchy's theorem from complex analysis, right? So once you know a little bit about the analytic properties of this generating function, using that, you can recover bounds, or you can say something about the Fourier coefficients, okay? All right, now, okay, so we need to understand the analytic properties of this. Yeah, and the analytic properties that we're interested in is not just no, holomorphy or integrability or differentiability of the function. It's something much more than that. Okay, so it has to do with how the value of this function is getting distributed on the upper half plane. All right. So yeah, so let's take a step back and look at the more classical example of such function, which is called the theta function. Okay, this was started maybe at late 18th century, early 19th century, by people like Abel, Jacobi, also Gauss. So theta z is sum of e to the power 2 pi. I missed the I over here, so it should be a 2 pi I n squared z, with n an integer. So you're changing, you're running over all the integers. So just a one-dimensional. Here we have three different dimensions. This is just like one-dimensional. So if you're looking at integer represented as a square, that this is the generating function, right? Okay, so the theta function is holomorphic on the upper half plane. That's quite easy to prove. I'm sorry, I'm missing the i's over here. So there should be a 2 pi I n squared z plus 1, 2 pi I n squared z, and 2 pi I n squared, right? It's easy to show that if you look at theta of z plus 1, then it's just theta z, because e to the power 2 pi I n squared is just 1, because n is an integer, right? And so we have a relation between the value of theta at z plus 1 and at z. Okay, and a much more difficult thing to prove, for which you need to use a little bit of Fourier analysis called Poisson summation formula, is that there is a relation between the value that theta takes at minus 1 by z with its value at theta z. So theta at minus 1 by z is equal to square root of minus iz theta z. Now you may ask, what do you mean by taking square root of a complex number? So that means you're just picking a branch of logarithm or square root. Okay, z is on the upper half plane, so minus iz is, I think, is on the right half plane. So you just take the usual square branch of square root, where the positive real numbers square root have positive real numbers. All right, so there is a relation of theta at z plus 1 and theta at minus 1 by z with the value of theta at z. Okay, this is related with what are called the fractional linear transformation in complex analysis. So if you take a matrix A, B, C, D in SL2Z and a point on the upper half plane, then we can define a new point. Okay, that's called the fractional linear transformation of Z when G applied to that. So GZ is AZ plus B by CZ plus D. So if you take G is in SL2Z or SL2R, then you can show that if Z is on the upper half plane, so is this AZ plus B by CZ plus D, right? So this gives you an action of this discrete group SL2Z on the upper half plane. This is something very standard in complex analysis. If you have done one course in complex analysis, you have seen this linear fractional transformations. All right. Now, there are particular two matrices that we're interested in, T, which is 1, 1, 0, 1, and S, which is 0, minus 1, 1, 0. Both of them are in SL2Z. That's very easy to see. And what's more important is that they generate the whole group SL2Z. That means any matrix in SL2Z can be written as product of T's and S's. Okay, so there will be some, these are the translations, because if you apply T to Z, then it gives you Z plus 1. And if you apply, this is the inversion. So if S is applied to Z, then you get not 1 by Z, because 1 by Z is not on the upper plane, but minus 1 by Z. So it's like S is the inversion map and T is the translation map. And this inversion and translation, they generate also all of SL2Z. Now, what we have seen so far is that the value of theta at Tz is related to value of theta at Z, and value of theta at Sz is related to value of theta at Z, right? Up to a simple function, because this you can compute very easily. Okay, and using the fact that these two matrices generate SL2Z, we can conclude that the value of theta at Gz is related to the value of theta z up to a simple function, which looks like this, right? So this type of functions on the upper half plane, which has this type of relation, okay, for all matrices in SL2Z are called modular functions. Okay, this is called modularity. All right. So now, the basic theta function, classical theta function, has this modularity property. And from there, you can show that the generating function that is related to the sum of three squares, okay, so this is the generating function. So this was the harmonic spherical function. Again, I'm missing I over here. Yeah, but the I is over here. Okay. yeah, so this generating function is kind of related to theta function. For example, if you take the harmonic polynomial to be the trivial one, the constant, say 1, then this generating function is a cube of the classical theta function. So the modularity of that follows from the modularity of theta. But if you take a spherical function of positive degree, then also you can prove using similar things, Poisson summation formula basically, that these are what are called modular forms. So there is a modularity relation for this, and they are actually what are called modular forms of weight k plus 3 by 2. So k is the degree of the polynomial p, and plus 3 by 2. Okay, I'm not going to the details. Okay, so there's something called modular forms of certain weight, certain discrete subgroup of SL to Z, and certain characters. So I'm just going to drop the mentioning this discrete subgroup of SL to Z, mentioning the character. I'm going to just say that there is a weight involved here, because the weight is something that appears in the estimate of the size of RPN, right? So this generating function for any spherical function P turns out to be what's called modular form of weight k plus 3 by 2. So it's a half integral weight because k is an integer, so k plus 3 by 2 is an integer by 2. So it's a half integral weight modular form. Theta is also a half integral weight. Right. So yeah. So the generating function falls in a class. It's a natural member of a class of functions. Okay, which are called modular forms of weight, half integral weight. Right. So the modular forms of half integral weight actually were started much before modular forms of integral weight. Because the theta function came much before theta and eta of Dedekind eta function. They were like classical things from 19th century that came much before Ramanujan started looking at integral weight. Okay, so this is something, one of the most important contribution of Ramanujan. So Ramanujan was very interested in partition function, understanding the partition function. I don't know whether he was actually interested in partition function or he was interested in the theory behind the partition function, because the partition function he used to relate different branches of mathematics. For example, he saw modular forms related to partition function. He realized, he developed a method called circle method to understand partition function, and he realized that the circle method is also related to modularity and so on. So, so maybe he was just using partition function as an example. So this is the discriminant form. It's kind of at the 24th power of the eta function of Dedekind. All right, so delta Z. Though, if you're familiar with the elliptic functions, then this is like the discriminant of the lattice. If you take the lattice with generator 1 and Z, where Z is an upper half plane, you get the elliptic curve. And if you look at the discriminant of the elliptic curve, it will be exactly this. Okay, so if you have some background from elliptic functions, the classical 19th century complex analysis, then you know what this is. Okay, and yeah, and if you drop this 24, then this is kind of the generating function of the partition function. You have to put an inverse though. Yeah, so delta 1 by delta Z inverse is related to the partition function. Anyway, so Ramanujan wanted to write this as a series. So he defined this function tau n, because this is just a power series, right? This is like product over n from 1 to infinity, 1 minus q n to the power 24. So you can write 1 by q n to the power, expand it into binomial using binomial theorem, and then take the product and collect the equal, terms with equal exponent, and then you can define this tau n. And Ramanujan was very interested in tau n, and it came to be known as the Ramanujan tau function. What was known is that this delta satisfies this transformation, or this is a modularity, right? So again, delta at some gz is related to delta at z up to a simple function. Here, the weight 12 appears, and that's why it's actually an example. Delta is an example of an weight 12 form. Forget about this one, okay? All right, and this was known already because of the theory of elliptic functions, but no one before Ramanujan actually considered this coefficients tau n, the Fourier coefficients. Ramanujan wrote down the conjectures. He looked at the tables of tau n, he wrote down his own tables of tau n. he conjectured that this tau is a multiplicative function. So if m and n are co-prime, then tau mn is tau m times tau n. And he wrote down a bound for h prime p, that tau p cannot be more than 2 times p to the power 11 by 2. Okay, these are the famous Ramanujan. He also wrote down how tau at p to the power k should be related to tau p to the power k minus 1 at p to the power k minus 2. Okay, so tau is a multiplicative function and it satisfies a recursive formula of degree 2. Ramanujan's first conjecture, this multiplicativity, was proved by Mordell just 1 year after Ramanujan proposed this conjecture. But the next, this bound for tau p took a long time, and a massive development in algebraic geometry, the Weyl conjectures and Grothendieck style algebraic geometry. And finally, Deligne proved this in 1974, probably. So it took a long time. Anyway, so Ramanujan was studying a class of functions which are related to theta function, which are related to the generating function. But there is a fundamental difference, because these generating functions are of half integral weight, and Ramanujan was looking at the integral weight. Okay, so there should be a relation between half integral weight and integral weight functions and modular forms. We are going to come back to that in a few minutes. But before that, Hecke gave a different proof of Ramanujan's multiplicativity conjecture, the first one. And he developed, and he perceived that there is a much deeper theory behind that multiplicativity property. Okay, that's called the Hecke theory. And using the Hecke theory, he looked at, so tau naught n is kind of a normalization of tau n, because tau p is of size p to the power 11 by 2, so you divide by n to the power 11 by 2, so to normalize it. And then look at tau naught n by n to the power s, so this is what is called an L function, of the L series related to the discriminant form. And Ramanujan's first conjecture says that this can be written in as a pure product. So this is a Dirichlet series, and this is an Euler product. And if you are familiar with Riemann's development of zeta function, so this is a picture of Riemann. So he looked at zeta s, which is the sum of, this is a Dirichlet series and also an Euler product. So this is Hecke's L function is an analog of that. But there is, of course, 1 has been replaced by tau naught n, where 1 is kind of a trivial function to us. Tau naught n is a highly mysterious function. This is a much simpler Euler product. This is a degree 2 complicated Euler product. So Hecke's L function is much more complicated than Riemann zeta function. And the main contribution of Riemann is that he realized that the modularity of the theta function is actually related to this functional equation of the zeta function. So zeta value at s is related to the zeta value at 1 minus s. Okay, so the modularity means theta of minus 1 by z related to theta z. That relation, it transcends to this relation of zeta. Okay? So there is a relation which between s and 1 minus s, and so it's kind of a reflection at the point half, right? All right, and Hecke was able to prove the similar type of things for his L function. He could prove a functional equation, and this functional equation for Hecke's L function is actually a consequence of the modularity of delta. Anyway, okay, so yeah, we need to introduce a little bit of complication over here. Instead of looking at the Hecke L function related to the discriminant form, we have to look at the twisted version of it. So what do we mean by twisted version? It means you take a character chi of z modulo mz, which is just a, it's a group character. For example, if you take m to be a prime p, then we have the quadratic residue symbol chi p. So chi p n is 1 if n is a square modulo p, minus 1 if n is not a square modulo p, and 0 if n is divisible by p. And in general, for if m is a square free number, I can define chi m to be the product of chi p's, which is called the Kronecker symbol or maybe Jacobi symbol. Okay, yeah, so we have, in general, we have characters for this group. In special type of characters are these quadratic characters, and we should be fine if you know a little bit of quadratic characters over here. So instead of looking at tau naught n by n to the power s, that's what Hecke had, we are going to twist it by chi n. So tau naught n chi n by n to the power s. One can show that we have an Euler product for that too, because of the multiplicativity. And Hicke could prove this functional equation, right? Again, relating the value at s with the value at 1 minus s. Okay, yeah, so really we have come a long way, but it's time to connect this with what we had before. Or as I said, that we always have this functional equation for this L function s going to 1 minus s. This is just a reflection at the point 1/2. So the point 1/2 is the center of symmetry. And the most important problem for us here is to understand the central value. What is the value of L at 1/2 at the center of symmetry when you take the discriminant form and twist by a quadratic character chi m? Okay, if you use the functional equation, and if you use the fragment Lindelof convexity principle from complex analysis, then it is very easy to show that this central value is bounded by square root of m. Okay, so I'm going to take m larger and larger, and I'm interested in how large this value is going to get with m, whether it's going to grow like m to the power 10 or e to the power m, something like that. But no, from functional equation, you can easily show that it's bounded by square root of m. And if you assume the Riemann hypothesis for this L function, then you can get the Lindelof hypothesis, which says that L function doesn't grow at all. So for any epsilon positive, you can bound it by m to the power epsilon. Okay. Yeah, so I'm not going to details about what I mean by less over here. So that's the standard notation in analytic number theory. Anyway, so we have an easy bound, root m, a known bound, and an unknown bound, a very strong bound for the L bound central value. Now, how is this related to the points on spheres? Okay, and here comes Shimura. So this is the picture of Shimura. You must have heard about Taniyama-Shimura conjecture, which was proved by Wiles in his proof of Fermat's last theorem. So Shimura gave a correspondence. So he was a person who related half integral weight modular forms with the space of integral weight modular forms. So recall that when P was a harmonic or a spherical function of degree k, then the generating function was of weight k plus 3/2. Now Shimura correspondence will relate this, will give you an integral weight, a 2 times k plus 1 weight function fp, small fp. And what is the more relation? Basically, it means that if you look at the Fourier coefficient of fp, which was rpn square, then that is related to the value, the L value of at half of fp twisted by the quadratic character chi n. So if you're looking at the nth Fourier coefficient, then you have to twist by the nth quadratic character chi n. Right, so that gives you, because you recall that in our problem we had to estimate RPN. We want to show that it is bounded by n to the power k plus 1/2 minus delta. And now we have related this. This is c is just a constant. You can just forget it because it remains constant as n varies. So as n varies, we know that the convexity bound or the trivial bound says that L half fp by n is bounded by square root of n. From there, I can get that Rpn square is bounded by n to the power L minus 1. Here, L is k plus 3/2, okay, the weight, half integral weight. N to the power L minus 1 times root n, and it comes out to be n to the power k plus 1. So the trivial bound for this central L value gives you that Rpn is bounded by n to the power k plus 1/2, which is just not enough for us, right? We need something less than k to the power n to the power k plus 1/2. And here you can see that any better bound for L half delta chi m instead of root m, if I have m to the power half minus something like m to the power epsilon, that will be fantastic. And then I can have something much better than n to the power k plus 1 over here, and that will give you the equidistribution. Okay, so the upshot is that Linux equidistribution conjecture will follow from a non-trivial bound for L half fp twisted by chi n. Okay, and getting a bound of this form n to the power half minus delta, that's what we want, is called a subconvexity problem. Okay, And as I was mentioned at the introduction, this is the type of problem that I work on. So yeah, so it's a long way from Ramanujan to here. But anyway, how do you prove something like this? All right. So from the functional equation for the L function, you get that L half, delta twisted by chi m. I'm just using delta and FP because delta is what Ramanujan was really interested in. It's very easy. So if you know how to do this, you know how to do this. Okay, so that's why I'm just taking delta as the prototype. So L half delta twisted by chi m is approximated by a series like this, tau naught m chi m by root m, where small n goes up to capital M. If you take a trivial bound for the right-hand side for this series, then you get the convexity bound and you're stuck. So the subconvexity problem is trying to get cancellation over here. And here the cancellation will come because the chi m is a character, so its value is just 1 or -1. So there is a lot of sign changes happening over here. And furthermore, tau naught m is also changing sign. So these two guys are changing sign. And I have to somehow show that these two functions are not related. So it's kind of showing that some correlation between two vector is small. Okay, and here is another thing that can be applied, and that was applied to solve this problem. And it also originates from Ramanujan's notebooks. Okay, it's called circle method. And the circle method is a Fourier expansion of the delta symbol. What is the delta symbol? Delta n is the function from integers to 1, 0. Delta n is 1 if n is 0, and is 0 otherwise. So it just detects the event whether something is vanishing or not. And Ramanujan had a way of writing down a Fourier expansion of this delta n, right? Okay, so this is, of course, Ramanujan. This is a picture of Hardy and Littlewood. After Ramanujan's death, Hardy and Littlewood developed circle method substantially to solve the wiring problem. And that's why it's called Hardy-Littlewood circle method. They developed a different variation of it. The type of expression that I wrote over here actually is it's a much modern version of the circle method. It's called the delta method. And this is due to these three people, Duke, this is Bill Duke, Friedlander, and Ivanich. And again, as mentioned in the introduction, Henrik Ivanich was my postdoc mentor, from whom I learned this delta method. Okay, and so this method was introduced, it was introduced and was used by Duke, Friedlander, and Ivanich to prove a subconvex bound for the central value, right? So instead of n to the power half, they have a 1 by 22 setting of that. And you can actually, yeah, so this is my way of doing subconvexity. We just use circle method directly to separate the oscillation tau naught m from chi m by just introducing a new variable over here, and then apply circle method directly over here. Okay, and that can also be used to get a subconvex bound. In fact, you can, if you use this, you can get a much stronger bound, m to the power half minus 1 by 8. All right, but going into the details of this proof will take us too far afield, and not going to do that. So with this, I'm just going to stop, right? Okay, thank you. Yeah. Mm. That is known for sum of 4 square. You have a way of finding out exactly how many ways you can write n as sum of 4 squares. So, yeah, for 3 it becomes difficult. Well, you only have a lower bound and also an upper bound. For if you have more variables, then you have more precise information about it, number of representatives. Uh, yeah, it's yeah, no, I mean the relation is not like that if you prove something about the Riemann zeta function, you may not be able to prove the same thing about the Hecke function. But what you expect is that they will have similar type of properties. Okay, so they are belong to the same class of functions, so they will have some type of properties. But there is no direct way to relate those two functions. So you cannot just pass on information about Riemann zeta function to the Hecke function, or information from Hecke function to Riemann zeta function. Thank you. Yeah, sure, sure. Yeah, I'll surely try. Yeah. This time it was a little difficult for me, but yeah, next time maybe. Yeah, sure. Thank you. Thank you.
Thank you, sir, for moderating the second session. We will now take a break for the lunch. Please enjoy your meal and we will recommence for a quiz competition at 2:30 p.m. in room number L105. Before that, I request everyone to come forward for a group photo.
Recording in progress. Recording stopped.
Except round 2. That also I will tell you, okay? Now, you can do your, you can see the total. Not now. When I say then, it should go like. Always 20 seconds now.
Invite
Just a
Dr.
second. We are going live, right? Let's start.
Okay, welcome again. I now invite Dr. Kuldeep Kumar Kataria for the coordination of quiz competition. Sir, please.
Okay. So I will request Dr. Rashman Mistry and Mr. Vivek to join me to help me coordinating this quiz. Okay, so see in this quiz competition there are certain rules. Okay, so can we go to the rules? Next slide. So just read this instructions carefully, all of you. So let me repeat it for you. Okay, so this quiz consists of a total of 4 rounds, and each round will have 2 questions per team. Each questions of another round will be of n points. So first round is of 1 point, second of 2, third of 3, fourth of 4. So if suppose you are not able to answer in first 2, 3, don't. Okay, so if you answer all the questions in the last round, then you may get. Okay. 0 point for wrong answer or for no attempt. Okay. Except the second round where there is a penalty of -1 point for a wrong answer. But if you don't answer, 0. Clear? For the second round. Read the questions carefully. I will not be reading the question. It's your responsibility to read. I will stay silent. Okay. So once the question is posed, timer will get on. Got it? So read the questions carefully and answer it verbally within a specified time limit. In case of a tie, the tiebreaker questions will be used after round 4. Okay? Use of course, any unfair means will lead to disqualification. Do you have the pens with you? No. No, we will not be giving. That's your responsibility. No, we cannot take it now. Okay, straight there. Can you give them pen? Can you just help them? Okay, one pen you can use. Which team does not have a pen?
1 point minus.
Okay, so next slide please. Paper you can do there. Okay.
question, okay? So who is the man in the picture? This is to everybody. Great Ramanujan. No, great Ramanujan is wrong. Yeah, so you have to answer precisely, okay? Don't do expectation. So next slide. The man who knew infinity. Okay, then so this is just was a warm up. Okay, so this is overview of the quiz. First round is visual. Okay. Second round is true and false. So visual, some image will be shown to you. So similar to like identify the mathematician or something like that. Okay. Second round will be true false. Third round will be multiple choice questions. Final round will be short answer type. Next. Okay, look, we are going ahead with the first round. So it's visual. So it will be 2 questions per team. Okay. 1 point for correct answer, 0 point for wrong answer or for not answer. Chocolate. So first question will be posed to team 1. Where is team 1?
Yes, sir.
Okay, ready?
Yes.
So whenever you say ready. Timer level. No. So go to the next slide. So it's 10 seconds for each question. Okay, in first round. 10 seconds. Okay, it's visual. For visual, you don't need to do the calculation. Okay.
So when time is over, so you will see
That's up to me.
the alarm sound.
So we are starting. Okay. So are you ready? Yes. You have to say ready. Then only I will pose the question. Ready?
Yes, sir. Ready.
Okay. So identify the method. Okay, time is up. So they answered G.H. Hardy. Also, I know the answer, but maybe. So that's not correct. I was just checking the cross checking. Okay, that's the wrong answer. Zero mark. I said you have answered G.H. Hardy. Okay, I didn't say that's the correct answer. Okay. So 0 mark. So now.
Opening is good.
Opening is good. Team 2, okay? So the next question will be team 2. No. Just a minute. Timer. You should say ready, okay? When you start. Okay, are you ready?
Yes, sir. Yes, sir.
Rasma, ready? Next. Time up. So no attempt, 0 marks. Okay. So he is S.R. Srinivas Vardhan. And the earlier one was Michael Francis Athia.
Sir, first term.
Michael Francis Athia. So that's okay. Okay, so team 3, are you ready?
Yes, sir.
So yes. Next. This is simple. Time up. Come on, this is Indian, Indian origin. He got field medal. Can anybody name? Come on. Akshay Venkatesh. Okay, so next question is pick 4. Are you ready?
Yes, sir.
Next. Okay, so they said, okay, I will not say answer. They said G.H. Hardy, that's a wrong answer. So he is Robert Langlands. Okay, team 5. Team 5, who is the leader? The leader is sitting quietly, okay? So are you ready? Yes, they are ready. Next. Okay, so time is up. This is like the most blunder you can do. This is the easiest one. Yes. This is Nina Gupta is the most famous. No, you didn't answer anything. I didn't. No, I didn't. Did you hear that? No, that's what I said. Time was over. You should be out. As a team, you have to say, come on. This is not a. Okay, I am the. Oh, don't worry.
Sir. Arguing with judge is -1.
Okay. No, you have to be loud. No? Come on, this is a quiz. This is not some, just whispering like this. This is not an exam. Okay. Team 6, are you ready? Team 6, where is the leader? Yes. You are ready? Okay. Okay, time is up. No answer, right? So, this is another very famous mathematician, very famous. He's a German mathematician, got field medal at a very young age. Can anybody name? No? Peter Scholes. Okay, team 7. Yes, Pradeep. Are you ready? Next. Okay, time is up. Another very famous mathematician who refused field medal is a very famous. Now, can anybody name? He refused. He got the field medal. He said, "I will not take it." Gregor Perelman is a very famous one. Okay. He's the only mathematician who rejected field medal. I told many times the story about that. Okay, so just warm up questions. Can go to next. I mean just fun. Okay, next. Permit Andrew Wiles, Permit last जो Professor Munshi का जो talk हुआ, his student. Professor Munshi is his field medal. Next. Riman. Next. Quick. Yes, Hardy. Okay, so now we come to part 1 view. Again, we will start with. Okay, team number 1. Now you have 15 seconds. Set the timer to 15. Okay. Team 1, are you ready?
This is also visual. This is also
You
visual.
will get the question. I will not read it. Are you ready?
Yes.
A different kind of visual. Okay. Okay, they are ready. Next.
What?
Time is up. So the answer is correct, but it was after the time.
Not after that.
Time was over. No bargaining. Okay.
Otherwise you will get -1.
No. Time was up.
Time is over and I said over.
So that's what I said. Time was over. Then you said. That's the meaning. Okay, so 0. Okay. Team 2, are you ready?
Yes, sir.
They are ready. Next. Okay, so 2 is the correct answer. Now see, I will not say right or wrong, even if it is correct. Once the time is over, then I will announce. Got it? So you give me the final answer before that time is over. Whatever you speak before time, I will take that answer. Okay? Again, I am the boss here, so whatever I decide. Okay? Okay, team 3. Are you ready?
Yes.
Okay, next. Time is up.
No, he said 40 earlier.
No, I got it. You said 40, but the answer is wrong. Yes, answer is wrong. Don't worry. Okay. What is the answer? 120. Okay, team 4. Are you ready? Are you ready?
Yes, sir.
Yes. How is the Josh? Yes. Next. Okay, time is up. You said 30. The answer is 40. Team 5. Are you ready? Yes. Next.
Nine.
I heard 9 now.
Three, sir. Three.
No. You heard. I heard 9 before the no. The final answer you said is 9, right? Am I correct?
Yes.
Am I correct?
Yes.
No. Please, let's go with the rule. Okay, it should come from the team. You should decide as a team. Okay. I said the last one I heard will be taken.
Yes, sir.
You change the no. अगर उल्टा होता तो क्या करते तुम लोग? No. Let's not argue on this. Yeah, I decided. Don't.
-1.
He was correct. 9 is not correct. So 0 1. See, you are a team. You are not individual. Please decide and tell a final answer. Okay? It's not individual. Okay, team 6. Are you ready? Where is the leader? Yes. You ready? Yes. Okay, they are ready. Next. Okay, it is correct. The most simplest. Okay, team 7, are you ready?
Yes, sir.
Yes, leader, are you ready? Okay, they are ready. Next. So I had 12 pi, and what do you think? Right or wrong? No. Yes, it's right. Correct. Okay, so we have a few more questions just for one. Go next. Next. ठीक है, time. Next. Okay, can you go to previous one? What is the name of the geometric object? No marks for that. Next. Next. Okay, so now we are coming to second round. Okay, so this is the final score after round 1. 1, team 6 1, team 7 1, and rest are at 0. Don't worry. It will be nth round as nth point. Okay, n points. So you answer both, then you can beat them. Don't worry. Okay, second round. Now see, 2 questions per team. It's true false. It's binary. Okay. 2.4 correct answer, -1 for wrong answer, 0.4 no attempt. So be careful. If I hear clearly true false, okay, then it will be taken.
Other team says, right, sir.
Okay, there should not be any ambiguity. Okay, be careful. It will come. Don't worry. Okay. Okay, if you want to say no, we don't want to attempt. Say it's no attempt. Okay, but before time. Again, the judgment is up to me. Okay, team 1, are you ready?
Yes, sir.
Next slide. So 20 seconds for each question. Okay. Ready?
Yes, sir.
Oh, no, team 1 answer. Okay, this is for team 1. Next.
True.
Okay, so is true. This is true. So 2 marks. Okay, team 2, are you ready?
Yes, sir.
Ready?
Yes, sir.
Okay, next. Okay, so they said false is correct. See, now you're equivalent, both of you are equivalent to 6 and 7, right? Okay, team 3, are you ready?
Yes.
Okay, next.
False. 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 False is the final answer.
Okay, time is up. Okay, you had a good comeback. So yes, false. It's an easy round. Yeah? Some everybody is scoring. Okay. So team 4, are you ready?
Yes, sir.
Okay, next.
False.
Okay, time is up. The answer is correct. False. Okay, team 5. Are you ready? Be louder, say yes now. Okay, next. Okay, time is up, so yes, it's true. Team 6. Team 6, are you ready?
Yes, sir.
Okay, next. Okay, good comeback. This is true. Okay, so team 7, are you ready? Okay, next. What do you think? What do you think?
What is true, sir?
Is not correct, is false. I mean, not saying it's false. The statement is false, but the answer is correct. Okay, so it's true. Okay, next. Next question. Anybody? Just open book. True or false? Quickly, quickly, be quick. No, just randomly guess it. It's false. Okay. Next. Next. Okay, now again 2B. We are going with 2B. Team 1, are you ready?
Yes, sir.
Ready?
Yes, sir.
Okay, next.
True.
It's true. Good, good. Okay. Team 2, are you ready? Team 2, are you ready?
Yes, sir.
You have to be louder, na?
Yes, sir.
Next. No attempt. 0 marks. By the way, it is not false, true. बच गए. Okay, team 3, are you ready?
Yes, sir.
Okay, they are ready. Next.
True, sir. Finalize, sir.
Okay, what do you think? On the set of rational numbers, set of rationals are always countable. How can correct? True is the answer. How come you say this is false? Who said false? Rohini, you said false? Okay, so 2 marks. Okay, team 4, are you ready?
Yes, sir.
Ready?
Yes, sir.
Okay, next. Okay, what do you think? It's false. Okay, so answer is false. Okay, team 5. Jagmohan, are you ready?
Yes, sir.
Okay, next.
False statement. Sorry. True. True, sir.
इसको बोलते हैं मौत को छुके वापस आओ. टक से छुके आओ. That's correct actually, sir. It's true. Okay, 2 marks. Otherwise you would have gotten it. Okay, team 6. Are you ready? Yes, where's Bhaskar? I don't see your leader. Your leader is sitting there. Okay, they are ready. Next. Okay, time is over, so it's false. Okay, team 7, are you ready? Last question to you for this round. Ready? Next. What do you think? Any other answer? Quick. It's not false, it's true. Minus 1. Next. This one? False. Okay, we are moving ahead with the third round. Okay, next. No, that was just for fun. Okay, now we are going to third round. Now the third round is MCQ type. 2 questions per team, only one option is correct. Only one, okay? 3 points for the correct answer, 0 points for the wrong answer for no attempt. It will come, it will come. So, next slide. 25 seconds for each question, okay? Okay? Team 1, are you ready? Yes. Okay, next. Okay, so I accept this answer. Option B is correct. But see, you have to say ABC. Don't say the same. Okay, Team 2, are you ready? Team 2, are you ready? Yes. Okay, next.
C.
Okay, C is correct. Team 3, are you ready?
Yes.
Okay, next.
B.
You said B. That is, what do you think? That's correct. B is correct.
No, none of the input, they said D. No, hey, come on, yeah. Sir, he said B. सर हम लोगों को श्योर नहीं था इन्होंने बोला बी मस्ट बी मैंने बोला था
You are see who is sitting close to him is verifying. He said there's a B. Other team.
Okay, fine.
Come on. And I also heard it.
Yeah, it's okay, sir. Fine, sir.
And see, I'm the judge here. Let me judge. I'm moderating this. Okay. Okay, team number 4. Are you ready?
Yes, sir.
And POD में भाई बोल देना बॉम्बे लैंग्वेज so that no it was clear to me, let it be clear to everybody. Okay, are you ready, team 4? Okay, next. Okay, I heard A, that's not correct. 0 marks.
Option B.
Option B is correct. Okay, so team 5, are you ready? Okay, next. What do you think?
Option C.
Okay, A is correct. Team 7, are you ready? Better you should take pen and paper, okay? Ready? Okay, next. Okay, time is up. At least you could, with the negative marking, you could have one. What do you think? What is the answer?
A.
D is the answer. D for Delhi. See, I have to correct you. Again, they are saying B. Okay. Okay, so just a second. Maybe we can go to the next question. Next. Just tell me what is the answer to this? Just fun, okay? Anybody? Okay, you can. Next. Okay, so now again, team 1. Are you ready?
Yes.
Okay. Next.
Yes, Matthew Brown. Directed by. Yes, Matthew Brown. B. Option B. Yes.
Oh my God. What do you think?
Yes, correct, sir.
Matthew Brown is correct.
Yes.
Okay, team 2. Are you ready?
Yes, sir. Yes, sir.
Okay. Here we go. Next.
Option is A. Option A.
Who said A? That's correct. Team 3, are you ready? Okay, next.
B for ball.
B for ball.
B for ball or D for doll? Bombay or Delhi?
22nd December. सर दे दो सर मार्क ये तो करेक्ट है
मैं लिख भी दिया। Team 4, are you ready? Are you ready? Team leader should say, are you ready? Okay, next. काश दिल्ली बोला होता okay, it's D answer. So
माइनस नहीं है ना
Michael Athias the first picture shown, and I also said in the beginning the field medalist. Come on, अगर सुन रहे होते तो बता सकते थे कि ये भी तो नहीं है. Okay, so team 5, are you ready? Ready? Okay, next.
Young Ritarata Munshi.
What do you think? Correct?
B Bombay.
Anybody?
I think A or C.
It's C. नाम दोहराई सुजाता. Okay, so It is paying number. B is the correct answer. They have prepared. Okay. You can really see from Wikipedia. Okay. Okay, team 7. Are you ready? Okay, team 7. Okay, next. Okay, what do you think? C for cat. 11. Okay, 0. Okay, so this is now, we are in the final round, okay? Can we go to the next question? So this is in which year Ramanujan elected in the final?
19.
See, there is no list of Ramanujan. It's 18. No, sorry, not 17, not 18. It's actually, yes, it's 18, 1918. See. Okay, so final round, okay? Now, can you tell the score, okay, just for total? So that, they can... Status, okay? Status as of now, don't write it. So, team 1 score is 8. No, sorry, 10. Team 1 is 10. Okay, team 2 is 9. Team 3 is how much? 10 again. Team 4 is 4. Very good. Team 4 is 4. Team 5 is how much? 7. Team 6 is 8. Team 7 is not, yes, it's 2. Don't worry. We have 4 marks here. 8 marks you can score maximum. And there's no negative mark. Let's have a comeback. Okay, so next slide, please. So this is final round. This is short answer type. Okay, you have to answer. Okay, you have to now see, while answering you have to be clear. Okay, what you are answering. Relax and answer. Okay. So again, it's up to me what I hear, and I'm very bad hearing. Okay, be clear. And final answer I will accept. Okay. Sometimes, if suppose a name of some person is asked, if suppose you just say the surname, not the first name, surname, then I will accept. But if you just say, let's say, Kuldeep, I will not accept that. But if you say Kataria, I will accept that. Okay? Got it? So, surname is important. Okay? Even if you don't say the full name. Full name is it's good. Okay? So, surname has to be correct. Okay? So, 2 questions per team, 4 points for the correct answer, 0 points for the wrong answer, or for no answer. Okay? So, are you ready, team 1?
Yes.
Okay, yeah. Next.
Instruction will come.
Yes, next instruction will come next. So 30 seconds for each question, okay? Okay, so are you ready?
Yes.
Okay, please.
Yes. Joseph. Minus 2. This is Sipahi, so minus 2.
Unfortunately, this is not correct. This is 2. You did mess up with the negative sign. It's 2. The answer is 2. It's 2. It's 2. Okay, so team 2, are you ready?
Yes, sir.
Okay. Next. I heard 4 before they, and it is correct. I heard the no after the bell, okay? Okay, so team 3, are you ready?
Yes.
Are you ready?
Yes.
Okay, next.
One.
Come on, this is. Yes, what is the answer? Simplest question you can have. This is E. And what should be the power also got infinity. E. Answer is E. After the answer. After the bell goes, you said that. Okay, so not accepted. 0 mark. So when in doubt, you should always go with your instinct. Okay? So yes, team 4, are you ready? Yes. Okay, go ahead. Next. Okay, time is up. What is the answer? 13 is the answer, yes. Team 5, are you ready? Yes. No, sorry, yes. Team 5, yes. Team 5, you ready? Okay, next. तो पहले वाले का I mean the previous question. This is 5. The answer is 5. Okay. Okay. Team 6, are you ready? Bhaskar, you have to be louder. You are leading them, right? Okay. So yes, they are ready. Next. Time is up, so any guess? Question is 6 and the answer is also 6. And the team is also 6. Okay, so yeah, wrong answer. Team 7, are you ready? Okay, let's have this 7 question. You saved this team, okay? Yes, that's correct. You are trying to mess us up. Last moment he said to finally this time. So yes, the answer is true. Please make sure what comes at the last, okay? See, they have said 2 initially, but then he said no, hold on. That's not correct. But then the very last moment I was trying to hear that yes, somebody said 2, okay? So that person said. Okay, so yes, so now we are moving to the second part of the last round. Next question. Next. Okay, so again 20. Yes, so are you ready?
Yes, sir.
Ready? Okay, so yeah, they're ready. Next. Time.
Last time
The answer is also not correct.
Sir, genius Ramanujan.
No. A life of the genius Ramanujan. Okay. Team 2, are you ready?
Yes, sir.
Are you ready?
Yes, sir.
How is the job?
Yes, sir.
Yes, sir. Okay, let's have the second question, please.
Rubber ka Munshi, sir. Munshi. Rubber ka Munshi.
Is it correct?
Yes, sir. Yes, sir. They don't know, sir.
That's not correct. Okay.
That's not correct.
It's not correct. It's Saket Sora from IMSC. Okay. He's a computer science. Person from computer science. Okay. Team 3, are you ready?
Yes.
Ready?
Yes.
Okay. So next.
Sir, fractional.
Yes. Bernoulli. You have not done that. It's Bernoulli. Okay. Team 4, are you ready for the last question for your team? Yes. Ready? Ready? Okay. Yes. Please. Next question.
23.
Okay, time is up. The lady is no more. She is one of the finest mathematicians in the world. She was actually. She passed away in I think 2016 or 17. Okay, so awarded was in 2014 actually. She's a very famous mathematician. Okay, so team 5. Are you ready? Ready? Jagan, come on.
Yes, sir.
Hey. Yes. Next, please. What do you think? Who can answer this?
Maybe Andhra Pradesh.
Who is from Andhra Pradesh?
Andhra Pradesh. I think Andhra Pradesh.
Andhra Pradesh is correct. हो गया, don't worry. They are more worried about other marks. This team one, okay. See, I told you are strong, that doesn't mean Okay. So, team 6, okay? Team 6, yes. Are you ready?
Yes, sir.
Ready?
Yes, sir.
Come louder. Ready?
Yes, sir.
Yes. So, yes, next. So I can believe that he is at least a Jacobi. Now, who was Jacobi? Jacobi was a mathematician. So he was comparing him with the lower, like least, his intelligence. So yes, that's correct. Jacobi is Now, yes, the favorite team, okay? Team 7, the last question of the quiz. Okay, everybody should keep silent. Okay, so are you ready? Pradeep, you have to be louder. Are you ready? Ready? No, I have no. So are you ready? Let's say everybody, cheer up for them. Are they ready? Yes. Are they ready? Yes. How is the Josh? Yes. How is the Josh? Yes. Okay. Hi. Okay, next.
Ramanujan.
Come on, it won't be that easy. The answer is, it's a very famous series goes by his name. Actually, he studied this infinite series. So it's a very, earlier work of, not Hardy, earlier work, like Newton's time. Have you ever heard of Wallis, John Wallis? The answer is John Wallis. So उनको वो लगाना था कि अनंत तक जाता है. अब कहाँ तक क्या लिखते हैं? Okay, so that's why he. The answer is John Wallis, so 0 mark. Now let's have a round of applause. So team 1 is 10. Team 2 is? Team 2 is 13?
Yes, sir. Yes, sir.
Oh my God.
Yes, sir.
That's 13, that's 13. Team 3 is 10. Oh my God, that's a tie. Team 4 is 4.
So you have to give special prize for it.
Yeah. Special mention will be there. Yes, special mention. Team 5 is 7. Team 6 is?
12.
No. 4 is 7.
12. 12, sir, 12.
12. Oh my God. Team 6 is. And team 7 is? 6. No, 6, yes. So we have the score, right? No. There's a tie.
Not right, sir.
There's a tie. We have a winner. Team 2 is the winner.
Yes, sir.
So first position team 2. Second position team 6. And we have a tie between team 1 and team.
Sir, दोनों को दे दो sir.
So there will be super over. Okay. Now we will go with the tiebreaker. Okay. We have this tiebreaker. Don't worry. We know this situation can come. So this is one now. So go to the next slide. The question here. Next slide. Okay. So only again it's a MCQ type of only one option is correct. Okay. So we are actually trying to decide here who is at third position. Okay. So the first question will be posed to team 1.
Sir, is there any negative marking?
No negative. There's not even a marking. Okay. It's just about who scores. So if there's a tie again, then again we will repeat this. Okay. First question is posed to you. So are you ready?
Yes, sir.
Just a second. So set the timer, na? Set the timer. So 10 seconds.
10 seconds.
Yes. You have 10 seconds to answer this. Okay. See, please don't disturb. Okay. This is crucial now. 10 seconds. You have to be very fast. Okay. Are you ready?
Yes.
Next.
Option D, one.
Option D is correct. Okay. Team 3. Are you ready?
Yes, sir.
And if he also take it. That's okay. Okay. So are you ready?
Yes.
Okay.
Set of rational numbers is counted.
C is correct. Oh my God. Okay, team 1 again. again, okay? Team 1 again, are you ready? Are you ready? Okay. Next. Time is up. At least you could have said something. The answer is A. Now team 3.
Yes.
You can create history.
Yes, sir.
Okay. Are you ready?
Yes, sir.
Are you ready?
Yes, sir.
How is the Josh?
Hi, sir. Hi, sir. Hi, sir.
I don't think so. Okay. Next.
B. 41B.
That's wrong. Answer is A.
Give it to both of us, sir. We'll share.
Huh?
Give it to both.
No, we cannot. No. मजा आ रहा है हमको. So okay.
We have enough questions.
We have enough questions. Until unless these questions get over, we will not stop. Okay, team 1, are you ready?
Yes, sir.
Are you ready?
Yes, sir.
Okay, next. Time is up.
Sir, we said already said 24.
No, time up.
Answer was correct, but time was up.
No, sir. No, sir. No, sir.
Time up. Time
I
up.
am here, no, don't worry, I am listening. So, team 3, are you ready?
Yes, sir.
24.
Next.
D. D. Delhi.
Not correct.
Sir, 24 we said, sir. No, sir.
पहली बात तो आपको ABC बोलना था, ठीक है? अभी don't fight like this, okay? You are behaving like a child. Now you are irritating me. मैंने पहले इंस्ट्रक्शन दिया था कि ABCD बोलने होते हैं, right? Don't talk like this. और वो भी तुमने उसके बाद बोला है, enough. No. नहीं वो नहीं करता.
ठीक है चलो.
Okay, so yes, make it fast. So team 1, are you ready? Okay, next. Time is up. Okay, so team 3, are you ready?
Yes, sir.
Okay. Corona next.
B. B.
B. Option B.
B. Bombay.
Bombay is correct. So we have okay, so I hope you enjoyed this. Did you enjoy? My strongest team पढ़ा दिया तुम्हें. But they prepared, okay, very well. Actually, big round of applause for. Actually, everybody, I can say based on all this, team 1 was the most prepared and team 7 was the least prepared. Okay.
What about us, sir?
Huh?
What about us?
You were going randomly. Team 4 was nervous and team 2 was more focused and team 5 वो तो अपनी मस्ती में थे.
Sir, if you take x equal to p and y equal to p square, then what about the GCD of x square comma y?
चलो बाद में तुम क्लास.
C correct. C p square.
No, that is verified multiple times. Don't worry, okay? Don't. We will say, okay? So, and what about team 6? What about team 6? No. What is the opinion about team 6?
भगवान की कृपा से आए.
Okay. So let's wind it up here. Okay. So thank you all, and it was very enjoyable.
We enjoyed a lot, sir. Thank you.
Sir, thanks. to Rajkumar ji and Vivek also.
Thank you, sir. Now I request everyone to proceed for the tea outside. So we will resume again for our next topic. प्रजापति, प्रदीप विश्वकर्मा, रोहिणी भगवानराव पोटे, okay, this is me, Manisha. संचिता सतपाठी, जगमोहन, बी साई वेंकटा कृष्णा, वामसी कृष्णा मामिदी, ऐश्वर्या अग्रवाल, कृपा सिंधु बिस्वाल, रंजित कुमार गाटला, मुदादा वेंकटेश, पाशाम नितेश रेड्डी, पीयूष लोतिया, नरेश कुमार एम, सूर्य नारायण दास, राकेश आर, मुकुंद कुलकर्णी, ऋषभ मिश्रा, ध्यान स्वर्ण जे, Alugonda Rajkumar, M.A. Ajim, Guruvulu Naidu, Konada, Kalyan Kiran Kumar, Mohan Sundaram K, Luri Leela Rani, Krishna Chaitanya Janpati, Aravali S.L.K. Gopalama, Joji Thomas, Padmini Sharma, D. Anjan Kumar Reddy, Uday Bhaskar, Thipe Swami L.R., I. Sudhakar, K.C. Anandhan, Virendra Singh Thakur, Mondi Thoka K. Prasad, Guru Raj Upadhyay, Nanditha Mandawa, Kelampudi Murali, Basa Aditya Manisai Pawan, Firoz Akhtar, Telapati Anuradha Devi, Srinivas Naka, Penki Ramu, A. Naveen Krishna, Dr. K. Sudharani, okay, thank you everyone. Let's proceed for the tea outside.
Sure. Can you hear me? Okay, good. Yeah, so that's what I'm trying. Yeah. Share. Can you see my slide? Yeah, okay, good. Full screen. View में. view है. And full screen mode. Okay. Yeah, fine. I'm ready. Hello. Hello. Yeah. So thank you so much, Dr. Mistry. I know him for a long time, and it's wonderful to be here with all of you. Unfortunately, could not join there physically, but hope to come there sometime. So I'm sure already you have had a lot of discussions on Ramanujan, but this will be another discussion on Ramanujan, his life, and some of his works. I'm not going to go deep into the thing. It's a common audience, so it is just to kind of bring in some memory. We want to go back to the life of Ramanujan and try to relate the kind of events that has happened to him and some of the works that has really made a huge contribution to the even in the modern mathematics, people use those. Yes. नहीं मैं नहीं गया हूं अभी तक. I'll just go. Yeah, okay. So that's my target is to really bring into you kind of talk about his life and side by side couple of his works. Is it okay? Now it's moving, no? Yeah. So so that's it. So this is the picture that all of you saw. Let me start with this one. It is, in fact, the picture on his passport, and in fact, it was with the request of Hardy S. Chandrasekhar, that Nobel laureate, physicist laureate, physics Nobel laureate, and he was very much impressed with Ramanujan, and he took personal initiative to find his passport, and that's how we got this. You are not viewing the slide? Okay, so I have to stop share and do it again maybe. Let me do it once more. I don't know, that time it was coming, but anyway, let's see. Okay. Okay, so this is the picture that is well known, and as I told you, it was in his passport, and that was later recovered by S. Chandrasekhar with request from Hardy, and it was restored. And Chandrasekhar, as I was telling that was a huge fan of Ramanujan's intelligence, his mathematics, and they were from the kind of same state, so they had a lot of interactions. So he was born on, as we know, December 22nd, 1887. It was A.I.T, and at that time it was Madras Presidency. British rule was there. He was born to Srinivasa Iyengar, his father's name, and Komalatmal, his mother's name. They were living in Kumbakonam, and Srinivasa Iyengar was kind of a clerk in a small shop, sari shop. And Komalatmal was mainly a housewife, but she used to sing sometime in the nearby temple, which I'll show you the picture, and that has had a lot of effect on Ramanujan. And they were a very modest kind of a family, poor, I would say. Somehow they were used to manage. Sometimes there was no food, so Komalatmal used to bring food from the temple. The temple prasadam used to be their food. And you may not know that Ramanujan had, in fact, two brothers. And that time, during that time, there was this smallpox outbreak. And both the brothers died in that one. And somehow Ramanujan survived that outbreak. So this is Ramanujan's house. And if you have not gone, any of you, the students, the teachers, I will tell you to go and visit there once. It's in Kumbakonam. And it's a national museum now, maths museum, which has been restored by Sastra University, and they maintain this house of Ramanujan. His initial study was at town school, and again, this is another museum, I would say. I have been there a couple of times, and this school, they have preserved all the memories of Ramanujan there. If you go to the classes, you will see. This is the school where he studied, and you must. And this school will be another thing to visit if you go to Kumbakonam. And he was an outstanding student, as all of us know, and he won many academic awards. And then he was awarded a scholarship for showing excellence in mathematics to go to college. College means, like FA, what they call it, like, 12th after 10th. And he started doing exploration in mathematics at that time itself. When he was in school at the age of 13, he discovered most of the trigonometric identities. He discovered, why I'm saying that, he did not know that those things were already known. And then, like any other researcher, like all of us, when you do some work and we find out later that that has already been done by somebody else, we feel sad. And Ramanujan was also sad that, he did a lot of work, but then that already shows his creative power that, he could do at the age of 13, most of the trigonometric identities by himself. So at the age of 15, in 1903, this book, why did I take this book? He received a copy of this book. This book is a synopsis of elementary results in pure mathematics by Carr. So you can see the stamp here. This is a library stamp is there. And why this book is important is that this book, contains about 6,165 theorems. One book is containing 6,165 theorems, and it was arranged very nicely, quite scientifically arranged, and with proofs. And actually, this book had effect in Ramanujan's notebooks, that the way he wrote the notebooks, it is exactly following the pattern that we see in this book. So, of course, research-wise also, this book helped him a lot, because he was looking at those identities, he was trying to do similar things. So this book, I would say, that ignited Ramanujan's passion for mathematics. And this was a major source of reference also for him, that it's already been done and what can be done. So this book always he kept, and this had a major effect into his research also. He recorded his findings in notebook by following exactly. So just was trying to write down that how he has written in the notebooks you have not seen, like this way, without really giving much of a proof. Unlike in that book, he used to write those identities in his notebooks like that, following that Carr's book particularly. So he got the scholarship, and then he took admission to Government Arts College in Kumbakonam. He got scholarship because he showed a lot of merit, a lot of talent in doing mathematics, and he got a scholarship. And then he took admission in Government Arts College. But then already he was addicted to mathematics. I mean, he was not interested in doing anything else other than mathematics. He could not give time to the other subjects and failed in most of the subjects and lost the scholarship in the process. And they were not, as I told you, that they were not well off at all. And this scholarship was a great help for them also in some sense. And that he lost the scholarship. In fact, after that, he in fact ran away from their Kumbakonam, and people found him. In fact, he came to Chennai, and he was in the station. Then somebody found him in the station. These stories are all there. These are not stories, true fact. And then helped him to get. One of them was kind enough and took him seeing his mathematics. The kind of mathematics that he does. Some of the people there helped him to get admission in Pachiyappa's College in Madras. Again, there he passed in mathematics, and he did only the problems that he was interested in. He did not even try the other things. Even in mathematics, he was interested to a particular kind of mathematics. And mathematics, certainly he passed, but then he failed in other subjects. Again, he gave his exam on 1906, but failed again. So never could pass that FA exam. And he did not get a college degree. He left that, traditional studies like college studies, and then he immersed himself into inventing new mathematics. He was living in somewhere in T Nagar, still then there in Chennai, and he was living in extreme poverty. His friends who visited him, they remember that, he did not have money to buy papers. So he used to write on the slate without writing the proofs and other things. He used to just note down the results that he had. So he was almost on the brink of starvation at that time. That time, in fact, he had a medical emergency also, and he was having no money to really get the operation done. And then one doctor, so always he found some help from somewhere or other, helped him without taking any money, and the operation was done, and he was okay at that time. But he continued his work. He continued researching on numbers, on various identities, formulas, and kept jotting it on his notebook, mostly without any proofs. You can see as there's a notebook, one page that I have put it here. And he was kind of living in an academic desert. No one could comprehend what kind of mathematics he's doing. And there were no mentors also at that time. So he was kind of not having anybody to tell what exactly to do, what to do with those results, and how to communicate those things to the world people. He was desperate. And some people suggested him to write to some distinguished English mathematicians. He wrote many of them, and most of them did not respond though. Then he wrote to G.H. Hardy in January 16, 1913. So this is not that letter, but this is just to show you how he used to write. And at the end, you can see, is yours, S. Ramanujan. So this is the way that he used to write. Hardy, he had written many letters. This is one of them, but this was much later. So that particular letter which he wrote to Hardy, there is a take off from Hardy's part that he went through the letter, and the letter tells like that I beg to introduce myself. He got a clerkship job at that time in some small port, with a very meager salary. Somehow somebody helped him to get a job, and somehow he was surviving as a clerk. I have no university education. He did not pass that FA degree. I have not trodden through the conventional regular courses, but I'm striking out a new path for myself. And the results I get are termed by local mathematicians as startling. That he starts his letter like that. Letter goes on about 7 to 8 pages of mathematical formulas. He wrote something that made people think he was crazy. In fact, he wrote to Hardy also that you might find me crazy, but I can show you how I prove this. This is that famous 1 plus 2 plus 3 is equal to minus 1 by 12 that he wrote. And he told that he did not give the proof here, but he told that he has a nice way to prove it. And in fact, this is one identity that it should not be called. It's not the usual convergence. It's something called zeta regularization is there. But you can place some, you can do with some assuming certain things also. Like you can multiply by 4 and then subtract, and then minus 3c will come. Right hand side, it will come like 1 over 3. And so c is actual sum. So it is minus 1 by 12 comes. But then you have to assume many things. But actually, properly, mathematically, it comes from zeta regularization. That there is a relationship between zeta function and eta function. And you write that identity, and then you evaluate that there's analytic continuation is there, because zeta is not evaluated at minus 1 unless you have the analytic continuation. And that in minus 1, this is the value, zeta value, but then it is after that zeta regularization. So not infinity. So usual sense, it is infinity. It is a divergent series, not even a positive number. It's a negative fraction. So many people thought that he is really not sane person. So those of us know Riemann zeta function, we know that a little bit, you have some analytic number theory background. You would find this was not shocking. Hardy, he was a number theorist, so he recognized the brilliance in connection to the work of Riemann. Ramanujan finally, found someone who understood him. So this is how the story, the collaboration started from there. Hardy went through the other pages, that particular letter, that 7 to 8 pages, as I told you, and found some of them are false. False, not, it's wrong. And some of them are already known. Okay, so the letter ended with this famous, the continued fraction that x is equal to 1 by 1 plus 1, this way. And then, adding or subtracting 1, you can easily find out that x is like minus 1 plus square root of 5 by 2. It's not that here, but he says that one, not this one is that, which is startling fact. But the next one, that the letter ended with this related problem, that's called Rogers-Ramanujan's Ramanujan continued fraction. This was invented separately by Rogers and Ramanujan, not at the same time, but both of them, the credit goes to both of them. So this is, you write this thing as R of Q. The previous one is when Q equals to 1. So it is like 1 by 1 plus Q by 1 plus, this is a continued fraction. Like Q, you can take like, this modular form, people who know that you can take Q as 2 power e pi I j. And so Ramanujan claimed that he can evaluate R of e to the power minus pi square root of n for any positive rational n. And he gave the formula also for that one. And there is this golden ratio comes here, phi and the phi here. So he just ended there without giving any proof that he can evaluate this one for any n, but in particular e to the power minus 2 pi r of that. R is actually the quotient of two other functions, g and h. And so this was later, people who know Rogers-Ramanujan's identities. So this is one of the most interesting results. In fact, it shows a lot of things about algebraicity of certain numbers and other things. So this has the major impact into this continued fraction theory and many other things, this particular identity. Hardy thought at that time this claim is out of the world. Hardy did not have any idea how to do it. And he invites him to Cambridge. Okay, so that's how it goes. So Hardy's take here is this one. They defeated me completely. That was the first letter that he wrote. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. What it is saying that if it is not true, then how will somebody get that nice expression on the right-hand side from the left side? So it has to be true. But then he did not give the proof at that time. So let's go to this temple. This is a little bit of this story, this Sarangapani temple, which has had a major effect on Ramanujan. This is a Vishnu temple. So whatever it is, he came out from Kumbakonam without informing his parents and all, but they never stopped supporting him for his pursuance of mathematics. And he was highly religious. And when he was in Kumbakonam, he used to spend most of his time in this temple, Vishnu temple. And even if you go to his house, as I showed you in the house, there's a window there. And he used to sit there, the table is still there. And he will be listening to these drums and from the temple. And he'll be looking at the passerby, whoever is crossing on the road, and he'll be doing his mathematics. If you go to the temple, which I went there, and after crossing the deity, you have to go upstairs. Usually no other temples they do allow, but here they will allow you. And you'll be amazed to see that the wall is covered with numbers. I tried to find 1729, it must be there, but I could not locate because it's full of numbers there on the up of it. So, this is another place where Ramanujan had spent a lot of time, in this temple and going upstairs there. So his marriage, which is also another very important event that had happened very early at he was 21, and Janaki Ammal, she was barely 10 when she got married, 1909. And then there was some ritual that at least one has to attain some age before she comes to be staying with him. So she lived with her parents till 12. Then she came and joined Ramanujan. He was then at that time was in Madras Port Trust. I told you the mega salary. And with Ramanujan's mother, Janaki Ammal joined him there in Chennai, in Madras. And Ramanujan was continuing his pursuit in research in mathematics. And when Hardy invited, so little bit about Janaki Ammal. So I was giving a talk on this National Mathematics Day somewhere. Then somebody commented when I talked about Janaki Ammal that, such a famous mathematician, but look at his wife. She just a nondescript person. Not exactly in that way, but that was almost like that. So I did some research on Janaki Ammal, and then I had to tell him that, you should know before first, and then you should make a comment like that one. She was great in her own way. After such a young age, she lost her husband. She was in acute poverty, but she used to work. She went to Mumbai. She used to work, and she used to help the orphan children for their education. And all throughout her life, she had done it. Only at the later part, almost when she's dying, the West Bengal government recognized that is Ramanujan's wife, and some money was given, some honorarium per month was given to her at the last moment when she was about to die. But a lot of things one can say for Janaki Ammal also, that she was a great lady. And with that, all these drawbacks, or financial drawbacks, social, the kind of a widow at that time, at so young, but still she continued to help the human beings. So that he got the call from Hardy to join Cambridge. That was in 1914 to study mathematics and to work with Hardy. And those days, what used to happen that, if you go to overseas, like crossing the sea or something like that, it was a very orthodox Hindu family that Ramanujan belonged to. So that was not possible at that time to get a permission from his family, because if he goes, then he will not come back. Like, something, you will be thrown out from your society or your dharma or something like that. So that was a complex problem at that time. And this is their family deity, this Thayar, Namagiri Thayar, the goddess, that he told many a times that, he had dreams, and, in the dreams, he had solved many questions. And this is the goddess that they used to worship, their family goddess. So he solved this problem in this way that, after praying the family deity, he declared that she has blessed the overseas trip. So family agreed with that one. And Janaki then was 15. Janaki wanted to go with him, but then, due to family pressure and all other things, he declined. And a decision not to take Janaki with him that he regretted later. I'll come to that. So now Hardy and Ramanujan had a complex relationship. If you have seen the movie, you can see that many a times they are fighting, and fighting used to go to the high pitch. So Ramanujan never bothered to write down a concrete proof because he never had a formal study of what is called school, college, university. So he used to think that this is very trivial, and most of the time he won't write the proof. Whereas Hardy was a true mathematician. And when we are trained mathematicians, we will not accept anything just by saying you have to really prove for it for us. Even if I know that it may be correct, but so long as you are not providing. So that was same problem was happening between Hardy and Ramanujan, and that at some point became a major source of conflict between them. Hardy tried to convince him that without a concrete proof, nobody in mathematical community is going to accept his findings. He kept on convincing Ramanujan that a common ground is required to talk mathematics, and that is the formal way to do it. He needs to go through a formal training. So this tussle went on for some time, and then at some point they started understanding each other. Ramanujan realized the importance of formal writing, and Hardy realized that he has a genius in hand whom he has to mentor. So Ramanujan wrote in total 30 research papers. There, some of them are jointly with Hardy, and most of them are independent research. And it was World War time, and England was also suffering because of that, and there was difficulty everywhere. And Ramanujan was working at Trinity College at that time. He was a pure vegetarian and was unable to eat any English food because most of the time it will be non-veg things will be there. So despite these hardships, the war was going on in the background. He had path-breaking results. He proved path-breaking results. And because of that, he was elected FRS, the first Indian to receive it. And due to malnutrition, he fell seriously ill, returned back to India. These are all well known. His illness became severe, and he died 1 year after returning back to India in 1920 at the age of 32. During his deathbed also, he continued to produce mind-blowing mathematics. Only one letter that he wrote to Hardy after returning back to India, where he explained the mathematics that he is doing, and he wanted to return back to England after being recovered, which never happened after that. So this is a little bit of story about Ramanujan's life, very crisp, very concise thing. But let us look at some of the areas that Ramanujan's mathematics has inspired for the future mathematics. To name a few, wild conjectures that was solved by Deligne, and he got Fields Medal. That has modular form played a big role, and we all know the Ramanujan's invention in that area. We'll come to that one. Then another one is called monstrous moonshine, and Richard Borchardt got Fields Medal in 1998 for this one. So this monster group is one of the groups. Is a very huge group. It's a simple group, and it's like 10 into 2 to the power 53, something like that. Its order. It's one of those rare kind of this thing. So there was some conjecture regarding this group, and it's some representations of this group associated to modular forms, and string theory and other things. And the kind of modular forms that was used there, like J function and some mock theta function that Ramanujan discovered, was useful in the proof. Of course, Fermat's last theorem, where his delta function played a major role, and which was Andrew Wiles. And then, of course, his work in deathbed, which he called mock theta functions. I was recently reading an article from Cambridge, one big physicist, and he was, of course, Freeman Dyson has also said that people should look at these mock modular forms, what are called mass forms, more closely. And if they can figure out more about it, a lot of things like black holes and superstrings and all these things that can have a lot of major impact. Okay, so let me go to a couple of gems, and you have to stop me whenever time, if you feel, because I know that people are tired from the morning lectures are going on. So you can stop me, I will finish. Couple of results that I want to give of Ramanujan, which is really mind-blowing, one has to say. Partition function, all of us know what is a partition function. It's like, for example, if you take a partition function of 4, it is 5. And this is the way you can write it. It's a very interesting function. It occurs in many, many areas, in physics, in condensed matter physics, in mathematics, also many areas. And you can see that how it grows. Just little example, people who are students and all. You can see how fast it is growing. P of 200, this number where 200 can be written. I mean, you can write it, partition it 200 in this fashion, non-negative integers. Then it is like 4 into 10 to the power 12, approximately. So it grows exponentially. So what is Pn? Like, can you give a formula for Pn? And that was, Ramanujan proved. And this exponential function plays a big role in string theory. That was some energy kind of thing, which is related to this exponential thing coming into this partition function here. So he proved that Pn is approximately 1/4 square root of 3 e to the power pi 2 power 2n over 3. This was a tremendous result along with Hardy that he proved. And it's not just this result, but that technique that they introduced to prove this one is called circle method. And even now, the circle method is one of the main tools in analytic number theory and combinatorics. That was first introduced in this particular result of Hardy and Ramanujan, where they estimated, approximately gave a formula for number of partitions of n. And these are the two beautiful congruences that Ramanujan had proved, and that has 3 of them. That has, given a plethora of works after that. Even now, people are trying to find out this kind of congruences. I'm saying, because exactly such beautiful congruence is very difficult to get. Nobody got it after that. For example, you take any numbers of this form. So these numbers are like 4, 9, 14, 19, 20. It is 4 mod 5. So if you apply the P function on that one, that it take any big number, whatever you want of this form, then 5 will always divide that one. It's a tremendous result. So this 5 and this 5. So he did by hand first calculations, and then he conjectured, then he proved few of them. So similarly for 7, you take this 7n plus 5 and take any number of this form. And if you apply P function on that one, that's the number of partitions. The number will be divisible by 7. This 7, and again you see this 7. Similarly for 11 also it holds. So these are of this arithmetic progression. These are these numbers. And for 7, we saw for 5, 7, and 11. So 11n plus 6 is also divisible by n. This was proved by Atkin, even though it was the other two were proved by Ramanujan, conjectured, proved, and this one was conjectured by Ramanujan, but it was later proved by Atkin. And the question is that why only these 3 primes? Why not for others, other primes like 13 and all? No, then he conjectured that for no other prime, such beautiful congruence will hold. And it was proved later. It appears there are no equal simple properties for any moduli involving primes other than these 3 primes. Look at that just by some computations by hand. Then he proves that one. Then he conjectures, makes such a conjecture that for no other prime, that such a beautiful congruence will hold. And that statement was later proven to be true. And this Rogers-Ramanujan identities, which I'm not going, I'll just pass through this one, which I gave a little glimpse of that one. This Qs are very important. Mod Q is less than 1. So you can write there's a sum and there is a product, and then he proved these identities, and then he gave a partition theoretic explanation in terms of partitions. These identities he explained, and that was one of the beauty, I think, not going into that one. Already some congruence number that I told you. And yeah, so a quadratic form is like that. All of you know, it's like this kind of thing. Degrees maximum, the degree is two variables. So 4x squared plus 2x plus y. So this is a famous theorem of Lagrange, which 4 square theorem, which tells you that every positive number, whole number, can be expressed as sum of 4 squares. Sum of 4 squares of this form, 1 square, 2 square, 2, like just 4 squares, no coefficient is here. So this kind of quadratic form series find is a particular kind of quadratic form that it expresses. It's a universal Z form. Any composite number, any whole number can be expressed as sum of 4 squares. So Ramanujan was asking this thing that in his classic paper he gave 55 more such examples, different kinds of forms. Some examples you can see. This is what Lagrange. Then he put this coefficient here. He goes on like 7. So he showed that these are also universal quadratic forms. But then this one, 8 d squared, does not represent all because it misses 7. And this paper was very important for later work, which was a very famous work called the 15th theorem. It was by Conway and Schöneberger, and the theorem is so beautiful that it says that you take some other kind of quadratic forms like positive definite integer quadratic forms. Then you ask the same question, that does it represent all integers? That means representing means given an integer, can you find its expression as a solution of this quadratic form? Like you find x, y, etc., a, b, c, and then it should be able to represent every positive number. It says that if it represents integers up to 15, then it represents all. That's why it's called 15th theorem, and then it was generalized by Manjul Bhargava and all. Not going, but this was again motivated from Ramanujan's work in that, finding quadratic forms which will represent all the integers. Okay, so not going into that one. This is the house I was talking about, and this is the window. There's a stool still kept there. You enter from here to his house, and you can see Shastra Institute takes care of this now. There's a library inside that one, and he used to sit here, listen to the drum beating, and the road is here somewhere just after this, and people will pass on, and he will be sitting here and doing his mathematics. This is supposed to be the most important work that Ramanujan has done, and which is still motivating lots of people to look into these things. It's called Ramanujan tau function. It has profound impact on several parts of mathematics, and not only in mathematics, in other sciences also. This is something called delta function. Is studied. You take this q is e power 2 pi I z, where this is a complex number with imaginary, it's in the upper plane, so that imaginary part is bigger than 0. So you take q, and you 1 minus q to the power n to the power 24. This 24 is important. If you take this product, then it is really not the scope of this talk to give a good motivation. But again, this has something to do with number of quadratic forms which represent. One can say that this function helps in determining number of ways of writing a given integer as a sum of 2r squares. In fact, 24 squares in particular. This is so 2 into r is 12 here. So 24 squares. Number of ways of writing a given integer as a sum of 24 squares. So that's also another motivation is there to really study this particular delta function. But his motivation was different. Delta z can also be written, this 2 pi to the power 12 is not there. So it's tau n by tau n q to the power n. There is a typo here. And this tau is called the Ramanujan tau function. It is just there's some nice properties there where you have such an expression, Fourier series expansion. These are called the Fourier coefficients. They're nice nice arithmetic functions. So this is tau function from a natural number. It's just an integer. And this tau function has nice relations, like with respect to sigma divisor function. This is simply sigma 11 is simply d dividing n, d power 11. You take all these, which divides n, raise it to the power 11 and sum them. And tau is that tau function just I told you. So look at that beautiful relation with the sigma function and tau function, which was proved by him. And so it has a generating function if you take it, and then x into 1 minus x2. This is the definition. And then this is this, this Pochammer symbol or something here there. So you can write this expansion here, and these are all the tau values. Okay. So tau 2 is minus 24, tau 3 is 252, tau 4 is here, tau 5 is here. So that's how he calculated all the tau values, not all, a large number of tau values. And by studying them, he predicted certain nature of this tau function, which, people say that this is the most fascinating work of Ramanujan, is that, he conjectured that it is multiplicative function. That means if you want to evaluate tau of 15, it is enough to know of tau of 5 and tau of 3. Simply the product when the GCD of n is 1. And you have this nice relationship with the higher power. If you know the prime powers of the tau value, if you know the previous ones, you can find the next one by using this nice relationship between tau p to the power r plus 1, tau p to the power r, and r minus 1 is the previous ones. But this one is the most, that, getting an upper bound of absolute value of this tau functions. See, conjecture that it is 2p to the power 11 by 2. So look at that, he calculated certain values of this tau function by using the generating series. He found those values. Then he conjectured that, it cannot be beyond this. The value of p, once you know for p, you know for other things. So this first two conjectures was proved by Mordell immediately after he announced those things in. And the third one, of course, was proved by Deligne much later, which I told you that while conjectures in a much more general setup. But this one especially it's not trivial from this wild conjecture. So he had to do a lot of work to show this one. And he got Fields Medal for that. Now there is a famous conjecture that's called Lehmer conjecture, that tau never vanishes. It is never zero. As you saw that in the previous year, that it is not zero, but actually it is not zero for any natural number n. That's a conjecture. We don't know how to do it, but people believe that. So you can see that the first one is 1, 24, 252, 174, and all these things. And this is a picture of that delta function which Ramanujan was considering. It's a this animation kind of thing. You can see the symmetries. So this is something called modular form. People know that one. I'm sure in the audience, lots of people are there. So this is a cusp form of weight 12, and you can see the symmetries that these forms have. So that certainly attracted Ramanujan to study this thing and study the properties of tau function. In fact, page after page, you can see he has calculated from his notebook again these tau values. He went on, spent a lot of time in finding these tau values for various natural numbers. And in fact, he proved that, curious but very beautiful congruence. And now, recently I was in a conference, I saw people are trying to generalize this congruence, generalize in the sense that this is for cusp form or so-called. So, and this is the coefficient of so-called Eisenstein series. So there is a relationship between the coefficient of a cusp form and that of some Eisenstein series. So can one generalize that one? So look at the tau n is simply sigma 11 and modulo this prime 691. Okay. This is again the divisor function, 11th power of the divisors of n, sum of that. So he could prove that one, this beautiful congruence. And I will end the talk with this famous taxi cab problem, which without that, never complete a talk on Ramanujan. So this is when Ramanujan was on very unwell, sick, and almost on the deathbed. Hardy came to it was in Putney, somewhere in nearby, Chennai, in Madras and Kumbakonam, somewhere there, in good hospital. He was there. He had, in fact, TB, severe TB. Those days, TB was not curable. And Hardy, just to, he went to the hospital and he wanted to make him a little bit energetic because he was not looking very energetic. Hardy was known to really do those things to all his collaborators and other things, that he was very energetic all the time. So what he told, that I remember once going to see him when he was ill at Putney. I had written taxi cab number 1729. I told you that this number people know all, and remarked that the number seemed to be rather dull. Doesn't have anything interesting about that one. So immediately Ramanujan replied that no, it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways. Okay, look at that, the kind of problems that he was interested in. So this is like 1729, you can express, and it's the smallest number as a sum of two cubes in two different ways. Okay, so this is that famous number, and if people can recognize that, so I want to tell you that it's not that he knew a magic or he was a magician that he could immediately come up. He was working in this kind of problem. You see, it's sum of two cubes. If you know Fermat's last theorem, it says that this sum of two cubes cannot be expressed as another cube of another integer. So he was actually trying to find out how much it fails. Look at that his kind of problems that he used to work. Well, I know that it cannot happen. And people believed Fermat's last theorem for a long time, even though it was proved much later. But then sum of two cubes, we don't, it is already proven for 3 that it cannot express as a cube of another integer. But then you might be interested in how much it fails. Is it failing by a very small number, like a 1 or -1 or a +1 or something like that? So he was interested in attacking that problem. And he in fact, this I want to put up that near misses. Like you see, 6 cube plus 8 cube is 9 cube, not 9 cube, it's -1. Like 135 plus 130, this is again cube. It is not 172, but just missing by 1. So here, I don't know whether you can see it. You can see that 1729 is there, that he was trying to get that how much he misses. Then, in fact, he discovered 2 different ways of writing 1729. And that's how he was remembering that thing. And his memory used to be extremely sharp. And, he remembered even at that time when he was almost bed, that still that he worked on that one. In fact, he characterized those numbers in this particular paper, that which will be missing by 1. And there's particular conditions on these coefficients that he gave, that writing this is in this way. So certain numbers will be possible to write as sum of 2 cubes, the cube with a very small margin, like not cubed, but missing by 1. So this is his deathbed. He wrote to Ramanujan wrote. This is the Trinity College. So this is the only letter he wrote when after he returned back to India, and this was 1920 already, as you can see. I'm extremely sorry for not writing to you a single letter up to now. I discovered very interesting functions recently, which I call mock theta functions. So theta functions, are holomorphic functions. It's just, you think, but mock means, it's not holomorphic. You're allowing certain flexibility there. Some poles you are allowing there, meromorphic functions. And they enter into mathematics as beautifully as the ordinary theta functions. So he himself called it mock theta functions. And it's famously known even now as mock theta functions. Large number of mathematicians are working in that area, in mock theta functions. These mock theta functions were a mystery till 2002. 1920, 2002, till the PhD thesis of Zweigars, and he showed that Ramanujan has discovered what is called mass forms. These mock theta forms are living up to Ramanujan's expectation. As I told you, one of the most active area in research in modern mathematics deals with these forms. And in fact, people have found, like Nono has written a nice paper on this mock theta functions and its relations with black holes. So century later, these formulas of Ramanujan will be used to understand black holes. Okay, this is a picture of with his colleagues at the University of Cambridge. You can see in the middle, Ramanujan is there. And let me end it by saying that the legacy is this, that talent can be found anywhere, even in the most unexpected and unforgiving places. To fulfill its potential, it must be located, recognized, and then properly nurtured. That's what Ramanujan's case shows. That's the legacy that we need to know. I mean, even we as the teachers and all, whenever we find somebody is interested in mathematics, we should try to help them and try to mentor such students, even if they are coming from very, very rural, very poor backgrounds. Thank you so much for your attention. Yes. Right. No, I mean, you want to know that if you want to study these quadratic forms, especially that what are the things you need to study? Yeah. I mean, these are called universal Z forms, So, it's always nice to invent such forms. And mostly, this, I don't know, certainly some number theory quadratic forms like, linear algebra has to be there. And then, some modular forms, because modular forms will come into the picture. And yeah, I think more or less that's the kind of thing, not much of geometry that you require. So mostly in number theory, some kind of modular forms will be coming into the picture. Combinatorics might come, but these are difficult problems. Like even this Lagrange's 15th theorem. Now you can ask the same questions in number fields. What happens where, in Zi and all, are there universal Z forms? Universal quadratic form. Universal means it will represent all the integers. Representing means every integer you take it, there will be some x, y, z, w such that you will be able to express in like x square plus y square plus z square plus w square, something like that. Yes. Yeah, it was a pleasure. I mean, just having meeting, seeing all of you, very nice. No, sure. And you're never invited, Rajkumar. No, I'm just kidding. Yeah, sure. I will certainly come. So let's promise next year at least, I will come once. Beautiful campus, I know. So just to go there and spend at least a couple of days with you people. Yeah. Any of you would like to visit SRMAP, please let me know. I think Rajkumar will be coming in January. Okay. Yeah. Yeah. Bye-bye. Huh? Take care. Yeah, sure. Yeah, sure. I'll send it to Rajkumar Mistry. Sure. Yeah, thank you so much. Yeah, bye-bye. Yeah, bye-bye. Take care. Yeah, January. Bye-bye.
Bose, Arup Bose, to come on the dais and felicitate the winners. Sir, here. ठीक है. So team 3. So team 3 is led by Manisha.
She's a PhD student here and we are all faculty members of different.
I sent an internal job here.
A big round of applause. Position 3.
Yeah, okay, sorry. So please, it should be like this.
Once again. So they will take the clap for everybody. First, second, third. Okay, so for second position, second goes to team 6. They scored a total of 12, double their team number. So 6 into 2, 12. So this goes to team 6. The team leader was Bhaskar. So Bhaskar is Dr. Ajit's past student. Okay. Manisha was my student. She is my student. Yeah. Big round of applause to team 6. with certificates. One photograph with certificates. Okay, now first position goes to team 2. So this is the team leader is Nitesh Prajapati. He is a student of Dr. Rajkumar Mistry.
Wow.
A big round of applause. Come on.
This is really heavy.
So they don't want to share the stage with anybody else. So they are like pulled us this far. Okay, no, you should not go into the picture. So this is hard earned. So big congratulations to team 1. Congratulations to Dr. Mistry also. Yeah, once again. Yes. Thank you, sir. Thank you, sir. Sir, just I would like to request, because we are just concluding, so can you have like 2 words with us, because we will be concluding after that. Maybe just share some, because it's very, very less chance we get to, hear from the.
This is very sudden, so I don't know what to say. It was very nice to be here, and like Professor Chakravarti said, I was never invited before, so I could not come earlier, right? So that's a hint. But I remember this is a very sad story. I came to Raipur, Bilaspur, Jagdalpur when I was not that big, that little. I think I was a research scholar at that time, so some family visit was there. So I remember traveling all night from Bilaspur to Jagdalpur by car, and those days, this was early 80s. So I also remember when we were driving at night. This was an all-night travel, and there were tiger left in front of our car and just went from one side to the other. I still remember that. But those days are gone. We have new days now. Okay, so I thank you again for coming here. The unfortunate part that I realized that Ramanujan was born on 22nd December, and at that time the I.I.T is already devoid of students. So I was jokingly asking somebody to do some research whether that birthday is actually correct or not. Whether we can shift it to January 1st week or something like that. Okay. Anyway, jokes apart, it was very nice to be here, and all the best to you for your future. Thank you.
Thank you, sir. So anybody would like to say 1 or 2? I mean, don't say that we didn't give any chance to this audience. But keep it short.
Yeah. So very good evening to one and all. Thank you so much, sir, for it's a great honor to be part of this National Mathematics Day. And I think that we are conducting in our campus, but thing is that as a participant, it's a great chance for us at the end of the day when we are last 15 days at that. So great learning from all the 3 lectures. Thank you so much, sir, for giving this opportunity to participate. And the quiz, it's really a great energizing us in our mind and going through the lot of different type of questions and answering all these people participation was very good. Thank you so much, sir, and it's a great organizing, sir. Thank you.
Anybody else? Okay. So thank you.
Okay, thank you, sir. And thank you, sir, to be with us today. So we value your presence here. And now as we come near to the end of this event, now I would like to invite Dr. Rajkumar Mistry to deliver the vote of thanks. Sir.
This is not working.
Hello. Hello. Okay. So before vote of thanks, so I would like to say something. Actually, when I was, I think, class 7, 8, I don't remember exactly. So one day I was on a shop. So वहाँ पर रद्दी पेपर होता है ना, तो एक महीने जो है पहले ये विज्ञान प्रगति निकलता था हिंदी में, तो उसमें एक मैगजीन था जिसमें कि वो पूरा रामानुजन का विशेषांक था, पूरा रामानुजन का ही उसमें था। तो जो है वो पूरा जो है वहाँ पढ़ा हुआ था। तो अब मैं उस टाइम जो बहुत छोटा था, मुझे जो थोड़ा हेजिटेशन हो रहा था जो कैसे उसको मांगूँ, वो मेरे लिए बहुत वैल्यूएबल था, क्योंकि मुझे नंबर थ्योरी में पहले से बहुत इंटरेस्ट था। मैं नहीं मांग सका, तो वो जो है मैं आ गया वहाँ से। लेकिन बाद में वो मैगजीन जो है मैं अपने जो मेरा एल्डर ब्रदर है उनकी लाइब्रेरी में मिला, सेम मैगजीन जो वहाँ पर आता, क्योंकि उन्होंने मेरे बाद शायद देखा, उन्होंने उठा के ले आए। तो उसके बाद मैं नंबर थ्योरी से बहुत इंस्पायर्ड हुआ उसका बायोग्राफी पढ़ने के बाद। तो प्रोबेबली ड्यूरिंग 10th or 12th, so I had written a poem, so that is around 184 that Paddy, okay. So that I would like to recite here, but not the complete. And that was later edited by my elder brother also. So some of the poems, so I will just select 22. So 22 December is also birthday of Srinivas Ramanujan. So 22 lines I have chosen. So I will recite, then I will conclude with vote of thanks. Okay. So poem is in Hindi, so if you don't understand Hindi, so I am sorry. Okay. Yeah. थे रामानुजन गणितज्ञ ऐसे जिन्हें विश्व समादर देते थे, जिनकी मोहिनी प्रतिभा के आगे सब विस्मित हो जाते थे। अंक ही उनकी दुनिया अंकों में खोए रहते थे, अंक ही उनका ईश्वर, उन्हें ही वह पूजते थे। हमारी भारत माता ने कितने रत्नों को जन्म दिया, उन रत्नों ने ज्ञान दीप से विश्व को प्रकाशमान किया। ईस्वी सन 1887 22 दिसंबर आया था, चिरस्मरणीय विश्व में सुंदर क्षण यह बनकर आया था। गौरवपूर्ण दिवस यह रामानुजन का अवतार हुआ, गणित के इतिहास में नई प्रतिभा का आविर्भाव हुआ। 5 वर्ष की उम्र में उसने अपना विद्यारंभ किया, अपनी प्रतिभा से शिक्षकों को चकित करना शुरू किया। गणित में सर्वप्रथम आना रामानुजन की अभिलाषा थी। अपर प्राइमरी कक्षा की फिर से आई परीक्षा थी। 42 अंक 45 में से अंक गणित में उन्होंने प्राप्त किया। 100% अंक प्राप्त न कर पाने का भारी पश्चाताप हुआ। दुख कातर हृदय उनका घंटों अश्रुपात किया, गणित ही उनका जीवन, गणित से बड़ा ही प्रेम किया। प्रथम शोध पत्र था उनका, नवीन और अत्यंत दुरूह, सामान्य पाठक के लिए वह न समझा गया अनुकूल। विश्व को उनकी प्रतिभा का अब जाकर आभास हुआ, कई गणितज्ञों से उनका सार्थक पत्राचार हुआ। सन 13 में जनवरी 16 को हार्डी को प्रथम पत्र लिखा। प्रमेयों से परिपूर्ण वह पत्र इतिहास में विश्व प्रसिद्ध हुआ। प्रथमतः हार्डी ने उनके शोध पत्र को समझा था, उनकी अनोखी प्रतिभा को अपार अलौकिक माना था। ट्रिनिटी कॉलेज में प्रवेश पाकर कैम्ब्रिज वे चले गए, अलौकिक प्रतिभा से सबको विस्मित वे करने लगे। 18 फरवरी सन 18 विश्व आज गौरवान्वित था। रॉयल सोसाइटी लंदन ने अपना फेलो मनोनीत किया था। मद्रास विश्वविद्यालय ने भी उनका समुचित सम्मान किया। गणित प्राचार्य का पद विशेष तत्क्षण उनके लिए सृजित किया। भारत की प्रतिभा, भारत की काया, इंग्लैंड उनके प्रतिकूल था। ठंडी जलवायु, गिरती सेहत, लौटना भारत श्रेयस्कर था। उस शोध भूमि को छोड़ उन्होंने भारत प्रस्थान किया। वहां पर अब शोध न कर पाने का उन्हें अत्यंत खेद हुआ। कैसे होते स्वस्थ, ईश्वर को यह मंजूर न था। गणित साधना को विराम देना रामानुजन को मंजूर न था। अंत समय भी मोक थीटा फंक्शन पर काम किया। घनिष्ठ मित्र हार्डी को उन परिणामों से सूचित किया। विकट संकट में नहीं झुकने वाले, काल को वे पराजित कर न सके। अपने अनगिनत प्रेमी जन को वे रोने से न रोक सके। सन 20 में अप्रैल 26 को वे ब्रह्मांड में समा गए। अपनी स्मृति को वे जनमानस में छोड़ गए। थैंक यू। ओके, So now we come to the concluding session. So with this, we come towards the end of this program. On behalf of the organizing committee, first I would like to thank our invited speakers, Professor Arup Bose, Professor Rita Munshi, and Professor Kalyan Chakravarti to accept our request and for agreeing to deliver a talk on this occasion. I thank all the faculty members of various schools and colleges for showing interest to take part in this program. Also, I would like to take this opportunity to thank Professor Rajiv Prakash, Director I.T. Bhilai, for his continuous support and encouragement to organize this event. I thank Dr. Abhijit Pal, the Associate of Department of Mathematics, Dr. Kuldeep Kumar Kotaria, DPGC Mathematics, for their enormous cooperation in the organization of this event. A special thanks is due to all the student volunteers, namely Manisha, Rohini, Vivek, Nitesh, Bhaskar, Anirudh, Pradeep, for their help in coordinating this event. Last but not the least, I would like to thank Mr. Nihar Ranjan, Assistant Registrar, Academics and Staff members, especially Mr. Kunal Waldekar, Mr. Vijay Chaturvedani, Mr. Ratnadeep, and Mr. Jagendranath. I also thank ITIS team for technical support, Media Cell for the publicity of the event, and Campus Safety team. Finally, I congratulate the Department of Mathematics, I.T. Bhilai, for successfully organizing this event. We look forward to host such events in future too. Thanks to all of you once again. Have a good day. Thank you.
Thank you, sir. It was a wonderful poem and concluding this session on a positive note. And thank you everyone to be present here. We hope you had a wonderful experience. Now I request you everyone to come forward for a group photo.
Well,